All right, question 1. An object feels two forces, one with a strength of 8 newtons to the left, one with 20 newtons to the right. If the object's mass is 4 kilograms, what is its acceleration? So as always, we're going to start off with our free body diagram. Then we're going to move into summing the forces, in this case horizontally, where the sum of forces is equal to the force applied to the right minus to the left. We're going to call to the right positive and to the left negative. And putting in our values here, we get an answer of 3 meters per second to the right. In question 2, there's a book whose mass is 2 kilograms. It's at rest on a table, and you are asked to find the magnitude, underlined, of the force exerted by the table. In other words, we're not worried about the direction. So we're going to do our free body diagram. It is at rest. There is no net force acting on it. Therefore, the force normal up is equal in magnitude to the force of gravity. So by definition, the force exerted by the table on the book is the normal force, which we've talked about in class, and this is always perpendicular to the surface. So let's go ahead and sum the forces vertically. Again, you're going to find that because there is no net force, force normal is equal to the force of gravity, or mass multiplied by the acceleration due to gravity. So force normal ends up being 20 newtons. Question 3. What is the mass in both kilograms and pounds of an object that weighs 500 newtons? Then you're told how many kilograms there are in 1 pound. Well, weight is the mass multiplied by the acceleration due to gravity. All right? And an object in equilibrium, the object is not moving here. Therefore, it's very straightforward to be able to develop an equation and divide the 500 newtons by 10 meters per second, and you get 500 kilograms or 100 pounds. Okay? Question 4, draw free body diagrams for the following scenarios. Okay, so you're given a number of scenarios with a ball and a stick man. So scenario 1, where it's at rest, we see that. Scenario 2, there's a force applied to the right, but we still have our vertical components of force normal and force of gravity. In the third scenario, we once again have force normal and mass gravity, which should also be labeled that over here. Mass gravity. And remember, when an object is moving, so it has a constant velocity, there's no change in state of motion, there's no change in velocity, and therefore no net acceleration. So C is the exact same free body diagram as A. Okay? And here we have a force of friction acting to the left. That's going to slow down the ball. So force of friction here. D and E were on inclines, so the force of gravity, or mass multiplied by the acceleration due to gravity, is straight down. Notice that force normal is perpendicular to the surface here. Okay? And then we have force of friction acting down in parallel to the incline. In the last scenario, the ball is coming down the incline. Notice how force of friction is now up and parallel to the incline. Force normal is at a 90 degree to the surface, and mass gravity is straight down toward Earth. Okay, so again, key points to take away here. Friction is always opposing the direction of the motion, and the force of gravity is not resolved into parallel and perpendicular components because you haven't learned about that yet. Question 5. A can of paint with a mass of 6 kilograms hangs from a rope. If the can is to be pulled up to the top of the rooftop with an acceleration, so it will accelerate, there will be a net acceleration up of 1 meter per second, what is the tension in the rope? Okay, and this is where I'm going to implore you to always try to conceptualize these problems and ask yourself, okay, what would the force of tension be in the rope if it were not accelerating? In other words, if it were in just hanging vertically or moving up or down at a constant velocity. Well, that would be 60 newtons. In this case, it's accelerating upwards, so it should be greater than 60 newtons. Let's find out. First things first, free body diagram. Force of tension is shown to be slightly larger than the force of gravity, which goes with our prediction of the force of tension being greater than 60 newtons. Okay, so we have a net external force, and this is going to lead to a change in state of motion or an acceleration. Summing the forces in the y or vertical direction and calling up positive and down negative, we get force of tension minus force of gravity equals mass times the acceleration vertically. We have an overall acceleration of 1 meter per second up, so that is now placed into the equation. Solving for force of tension, we get 66 newtons, which is indeed greater than 60 newtons as predicted. Question 6. A bucket of water with a mass of 4 kilograms hangs from a rope. If the bucket is to be pulled to the top of the rooftop at a constant velocity, underlined, of 1 meter per second, what must the tension in the rope be? Remember, class, if it's a constant velocity, this object is not accelerating, therefore there is no net external force. So the tension in the rope is simply going to be equal to the force of gravity. And as we can see by summing the forces here, force of tension is 4 kilograms multiplied by 10 meters per second, or 40 newtons. Question 7. How much tension must a rope have to lift a 50 Newton object with an acceleration of 10 meters per second? So now this object is accelerating upward at 10 meters per second. So let's make a prediction. The 50 Newton object, if it were hanging or moving at a constant velocity, would have a force of tension of 50 newtons. But now it is accelerating up. Therefore, we would predict that the force of tension would be much greater than it would be when it was in equilibrium. So on your free body diagram, we have the force of tension shown to be significantly greater than the force of gravity. If we go through and sum the forces on this problem, we'll see vertically that we end up getting a force of tension that is not only greater than, it's twice as great, which should make sense if we're calling the acceleration due to gravity of 10 meters per second, yet there's a net external force leading to an acceleration up of 10 meters per second. So the force of tension in the rope is double what it would be if it were in equilibrium. Question number 8. A pair of fuzzy dice is hanging by a string from the rear view mirror. You speed up from a spotlight. During the acceleration, the dice do not move vertically. However, the string makes a 22-degree angle from the vertical. You're given the mass of the dice, and you're told to sum the forces in the horizontal and the vertical direction to determine the acceleration. Now remember, the acceleration here is happening in the x or horizontal direction. Okay, so a scenario very similar to this one here. Okay, where the acceleration in this case is off to the right, and you can see the angle here from the vertical forming. Okay, so you could actually draw in some additional information here, and of course theta is there. All right, so we're going to need to use trigonometry to resolve the force of tension F sub t into its vertical and horizontal components. All right, let's look at our free body diagram. So here we have force of tension, and it's shown at an angle. And as you've learned in class, anytime you draw a free body diagram and you have its vector components, the forces are not resolved. Redraw the free body diagram showing the resolved forces. So in free body diagram 2, we have something that looks like this, where we have now resolved force of tension X, force of tension Y. Now we're going to sum the forces vertically. Okay, so it's the force of tension in the Y. If we're calling up positive and down negative, so force of tension Y minus the force of gravity is equal to the mass times the acceleration vertically. Now, the dice you are told they're not moving vertically. There is zero acceleration. Therefore, force of tension Y is equal in magnitude but opposite in direction of the force of gravity, or mass times the acceleration due to gravity. Let's look at the horizontal piece now. Okay, so we have the force of tension in the X, and nothing else is exerting a force horizontally on the dice. And so the force of tension in the X is equal to the mass times the acceleration in the X. It's the acceleration in the X that we're trying to find. So now we have two equations that we're working with. All right. So again, if we look at our geometry here, we're going to be using trig. And in this case, our angle is from the vertical. So we're going to use cosine for the force of tension in the Y, and we're going to use sine for the force of tension in the X, given that we have a resultant vector overall of the force of tension, which is the hypotenuse of the triangle here. Okay, so if we put in this trig here, we get these expressions. And now let's go ahead and see what we can get from this information. So here it is all laid out. Again, this is what we were able to determine. And we have our equations, our summations here now with the trigonometry. So in the vertical direction, if we rearrange and solve for F sub t, we get that F sub t is equal to mass gravity divided by cosine 22, which gives us 1.1 newtons. Okay, so we're using the vertical component here, and we're able to solve for the overall force of tension, which means we can now take that and put it into our horizontal summation. And by doing that, we get 1.1 multiplied by the sine of 22 degrees. We know the mass. Now we're able to simply solve for the acceleration horizontally of 4.1 meters per second per second. Now in question 9, you're told, or asked rather, how would the tension in the string change if the angle from the vertical increased? Okay, so if you had a greater angle theta, and as we've talked about in class, it is okay to make up numbers. It is permissible, encouraged rather, to use a semi-quantitative approach in this course, so you can make up numbers to justify a response. And that's what we're going to do here. So you don't want to choose a number that's like really close to the one in the problem. Make it so that it'll be a very clear distinction of how a greater theta. So like 60 degrees. And then we're going to plug in this value that we made up to justify our answer in this question. And we see that the force of tension has gone up from 1.1 all the way up to 2 newtons. So force of tension is increasing as the angle of theta increases, okay? I also want you to notice that acceleration in the horizontal must also increase because the force of tension is directly proportional to the acceleration. However, it is inversely proportional to the mass. So this should make sense. If the vehicle is accelerating at a greater magnitude, then the dice are going to swing, make that angle theta. It's going to be a greater angle theta because the vehicle's moving off, say, to the right with a greater acceleration, okay? Which means the force of tension is also going to increase, okay? And here you can see numbers here just plugged in to show this relationship that in this case here, the acceleration horizontally 17.3 meters per second per second. Okay, so big difference here. In question 10, you have two forces, F1 and F2, applied to a block. It is on a frictionless, I'm going to underline that, horizontal surface as shown below. If the magnitude, I'm going to underline the word magnitude, of the block's acceleration is 2.0 meters per second, what is the mass of the block? So we're trying to find the mass of the block here. Just looking at our diagram here, it should be fairly straightforward to then draw a free body diagram. Notice force 1 is, the arrow is greater than force 2 because force 1 is greater in magnitude than force 2. So we always want to try to represent that on our free body diagrams. So looking at this now, we can say the net force will cause an acceleration to the left. Hopefully that's evident. There is a net external force, and that force will lead to an acceleration of the block. Okay, so let's sum horizontally. Let's call right positive and left negative, as we typically do, but we will learn that we don't always have to do that. So we get 2 newtons minus 12 newtons, and that's equal to mass times the acceleration of the block, which we're told is 2 meters per second. And we've conceptualized that that's to the left, which is why it is now negative. So solving for mass, which is a scalar quantity, we get 5 kilograms as our answer here. All right, question 11. A 0.15 kilogram baseball is moving at 20 meters per second and is stopped by a catcher in 0.010 seconds. Find the average force to stop the ball. So initially we have a projectile motion problem. So let's look at what the free body diagram would look like for the projectile. I want to reinforce this again. So for an object in projectile motion, when we neglect air resistance, there is one force acting on the object, and that is the force of the earth on the ball or the object. In this case, mass times gravity. Okay? So, however, the second part of this, it's really a dynamics question because you're being asked about the force to stop the ball. So let's look at what's occurring at that point. So if we assume the ball is moving to the right, then the catcher would apply a force to the left. So we're going to call that the force applied, and we've shown here on the free body diagram that it is to the left. Let us sum the forces. So the sum of the forces in the x is equal to the force applied, which equals mass times the acceleration in the x. All right, so we only have one force acting, and that force is the force of the catcher, and the catcher's mitt acting on the ball. Okay, so if the ball is moving to the right, the force is acting to the left. All right, now what we have to do is we don't know force applied, we don't know acceleration, so we have to have another equation. We have one equation, two unknowns, or we have two equations. We can solve for one and plug it into the other, and we have enough information. We're going to use UAM and kinematics to find the acceleration of the ball. So in its simplest form, acceleration is change in velocity over change in time. The final velocity is 0 meters per second. The ball is initially moving to the right, okay, at 20 meters per second, and we're given the change in time. So we get an acceleration, a negative acceleration of 2,000 meters per second, which makes sense. Look at the denominator, 0.01 seconds. So this object goes from 20 meters per second to 0 meters per second in a fraction of a second. Now we know the acceleration, so let's plug that into our force summation. Keeping our signage, we get a final answer of the force applied is 300 newtons to the left, or we could say negative 300 newtons. Question 12, a 25 Newton force that is northward and a 35 Newton horizontal force that is southward act concurrently on an object which is on a frictionless surface. What is the magnitude of the object's acceleration? I'm going to underline the word magnitude. I also want to clarify here, these are horizontal forces. They're acting horizontally. There's no vertical component. So we're looking at one occurring heading basically north, which is force applied 1, and the other one south, which is force applied 2. Notice that force applied 2 is greater in magnitude than force applied 1 and is indicated as such on the free body diagram. Summing the forces horizontally, we get, if we call up or north, positive, and down or south, negative, we get force applied 1 minus force applied 2 equals mass times the acceleration of the object. So plugging in our numbers here, along with the mass of the object and solving for the acceleration in the x, we get a negative 0.67 meters per second. However, the question only asks for the magnitude of the acceleration, so the final answer, 0.67 meters per second. Okay, now, question number 12, a cardboard box of mass m is on a wooden floor and is represented by this free body diagram. Okay, a force is applied to the left. Given this information, derive two expressions that are accurate representations for the box. If we translate this problem is simply asking you to sum the forces vertically and horizontally. So let's go ahead and look at that. If we look at the x or horizontal direction, there's only one force. That's the force applied, and it is acting to the left, so the force applied equals mass times acceleration in the horizontal direction. In the vertical, if we call up positive and down negative, we have force normal minus mass times gravity, or the force of gravity is equal to mass times the acceleration vertically. Question 14. You apply a force to an 8 Newton you apply an 8 Newton horizontal force to a 1 kilogram book that is at rest on a horizontal table. If the force of friction acting between the book and the table is 4 newtons, A, what are the magnitudes of the forces on the book? B, what is the acceleration of the book? So we haven't gone into too much depth about force of friction. However, you should know that the force of friction is opposing the motion of the object if it's moving. Okay? All right. So with that in mind, let's look at the magnitudes of the forces acting on this book. We have in the y direction, we have force normal, okay? And that is the perpendicular force of the of the table onto the book, and we have the mass gravity, which is the force of gravity, which is the force of the earth downward on the book, okay? Horizontally, we have the force applied, which is to the right, and the force of friction, which is to the left. Now, we're assuming this book, there is a net force horizontally, and that the force applied will result in an acceleration to the right. So on your free body diagram, you can see here that the force applied is greater in magnitude than the opposing force or the force of friction. Okay? All right. So if we look at the forces acting in the x direction, we have, and we call right positive, left negative, we have force applied minus force of friction equals mass times the acceleration in the x. Now, if we look at the forces vertically, we have, and we call up positive, down negative, we have force and normal minus mass times gravity is equal to mass times the acceleration vertically. However, this object is not accelerating vertically, therefore there is no net external force acting vertically, which means that summation equals 0, and therefore force of normal is equal to the force of gravity, or mass multiplied by the acceleration due to gravity. So force normal here, when we plug in our values, we have 1 kilogram times 10 meters per second. So we have a value equal to 10 newtons, which should make sense. Let's look at part B here. Part B, we're asked about the acceleration of the book. So if we look at our summation horizontally and we plug in our numbers, we have 8 newtons minus 4 newtons. So notice force of friction's opposing the motion. That's why it's being subtracted. Equals 1 kilogram multiplied by the acceleration horizontally. Solving for the acceleration horizontally, we get a 4 meters per second per second. Question 15. A 500-gram cart is released from rest. And I also need to change this to base SI units on a horizontal track, and it travels 75 centimeters in 1.75 seconds while experiencing an average horizontal applied force of 0.5 newtons. What is the magnitude of the force of friction between the cart and the track? All right, let's start this one off like we always start these off, with a free body diagram. And we have 4 forces acting. We have force normal, the perpendicular upward force. We have force of gravity, which is down toward the earth. We have a force applied to the right, and we have a force of friction opposing the force applied, and the force of friction's to the left. Notice force applied is slightly larger than the force of friction, which would lead to a net external force and therefore an acceleration horizontally. Okay, so converting some of these to base SI units, we're going to need to find some information out here because we're going to find that we don't have enough to go off of. So let's look at our summations here. Force applied, if we call it to the right positive, minus force of friction equals mass times acceleration horizontally. Vertically, because there is no net external force and therefore no acceleration vertically, force normal is equal in magnitude opposite direction of the force of gravity. Now, let's go back to Unit 1 and use a UAM equation. So we need to convert these values into base SI units, in other words, meters and kilograms. So the UAM equation that works well here is the change in horizontal position is equal to the initial velocity multiplied by time. However, as I've underlined in this problem, the initial velocity is 0 because it starts from rest, so that piece goes away. And so we are left with 1/2 multiplied by the acceleration and time squared. Solving for the acceleration in the x direction, you get 0.4 0.49 meters per second. So that's going to be an acceleration to the right. All right, so now that we have that information, we can look at our horizontal summation. We now know the acceleration, which means we can plug in values and solve for the force of friction. The magnitude of the force of friction is 0.26 newtons. Question 16. A 20 Newton force due north and a 20 Newton force due east act concurrently on an object as shown in this diagram. What additional force is needed to bring the object into a state of equilibrium? Okay, a state of equilibrium, meaning it is not moving or it has a constant velocity. So let's look at that real quick here. This is really vector addition. We're going to use tip to tail vector addition, and we're going to look at the equilibrant, which is going to be basically opposite, equal in magnitude and opposite in direction. So if we do that here, we have our north vector and our east vector. We can rearrange these and use tip to tail vector addition. The blue resultant vector is the hypotenuse of the triangle. So that is the overall resultant force acting on this object. Okay, so we have an isosceles right triangle. So hypotenuse being equal to 2 multiplied by the square root of 2, where we have 45-degree angles. And so we can also now use the Pythagorean theorem to find the hypotenuse or resultant vector. In this case, it's equal to 28 newtons. And the cardinal direction in this case is northeast. Okay, so remember, if it's at a 45-degree angle, we can simply say northeast. So what does that mean about our vector, our force that we'll need to bring this to a state of equilibrium? Equal in magnitude, 28 newtons, opposite direction, southwest, which is a 45-degree angle southwest. That force will bring this object into a state of equilibrium, which is either a constant velocity or no motion, velocity 0. Okay. Question 17. A 1 Newton metal disc rests on top of an index card that is balanced on top of a glass. What is the net force acting on the disc? Okay, so let's take a look at what's happening here. Here's the free body diagram for the metal disc, which is on the index card, which is on top of a glass. We have force normal acting perpendicular to the system or surface, and we have the force of gravity straight down toward the earth. And again, that force normal is perpendicular to the surface. Okay, so we're asked about the net force. So the overall summation, and this metal disc, it's resting on top of a card on the glass. So there is no net external force, and thus we find that the answer is simply 0 because there is no acceleration, no external net force. So the answer is simply 0 newtons. In question 18, a 15-kilogram wagon is pulled along a horizontal path to the right with a rope that makes an angle of 30 degrees above the horizontal. The tension in the rope is 100 newtons. So that means that our hypotenuse here is 100 newtons. The rope is at 30 degrees, as I said, and a frictional force of 20 newtons to the left, remember, it's opposing the direction of motion, is acting simultaneously. Part A, what is the acceleration of the wagon? So that's asking us what is the acceleration of the wagon to the right, horizontally. Part B, what would happen to the frictional force if the angle increased from 30 to 60 degrees. Let's start with part B. Let's start with what we know. Let's start with free body diagrams. So we have a force of tension acting at an angle of 30 degrees. So we're going to need to resolve the force of tension into the horizontal and vertical directions using some trigonometry. All right, so free body diagram 1 is showing that resultant 100 Newton vector. And we also have the force of friction acting to the left horizontally, along with force normal and the force of gravity acting vertically. And they're going to be equal in magnitude, opposite in direction in that case, since the wagon is not accelerating vertically. There's no net external force acting vertically. Okay, so let's see if we can get an answer here. All right. First, we're going to need to then redraw the free body diagram once we've resolved the components. Remember, if you're going to draw your free body diagram with unresolved components, that's fine, as I've done in free body diagram 1. But you need to resolve that. So when we resolve the force of tension into X and Y, we need to redraw the free body diagram showing the resolved forces. Okay, so you can see free body diagram 2, I've done that. We now have force of tension X and force of tension Y, along with our other forces acting on the wagon. Okay, time to sum the forces. Let's start horizontally. Okay, let's call to the right positive, left negative. So we have the force of tension in the X direction. Remember, we need trig. Minus the force of friction equals mass times the acceleration horizontally. Vertically, we end up with the force normal being equal to the force of tension. Okay, let me restate that. Vertically, we end up with the force normal plus the force of tension vertically being equal to mass gravity. In other words, we have two forces acting vertically upward, and we're calling up positive and down negative. So again, force normal plus force of tension in the y direction minus mass gravity equals 0. Therefore, force normal plus force of tension vertically equals the force of gravity, or mass times the acceleration due to gravity. All right, so now we can look at finding a solution to part A. So with our trigonometry here, you can see the force of tension in the X, which is here. We're going to be using cosine. So 100 cosine 30 will give us force of tension horizontally. All right. And then minus the force of friction. And we're told the force of friction is an average frictional force of 20 newtons to the left. So we end with an expression here, horizontally and vertically, same thing, okay? We have the force normal plus that vertical component, which we can get using, this is opposite of our angle, so we'll use sine. 100 newtons sine 30 degrees will give us the vertical component of the force of tension. So when we plug in numbers here for the horizontal, we end up getting a value of an acceleration of positive 4.4 meters per second, or 4.4 meters per second to the right. Okay, so all we've done there is plug in our values from the trigonometry, and we knew the mass, and that gives us the acceleration horizontally. Okay. Now for B, what would happen if the frictional force changed? So this is a really cool question. And the answer to it lies right here. Okay. Notice that the force normal, and now we're adding this force of tension Y. Well, the greater the angle is above the horizontal, say from 30 to 60 degrees, there's now more of a vertical component, okay? So FTY, the vertical force of tension, will increase, okay? So if we plug in that angle of 60 degrees and solve for the force of friction, we're going to see that the frictional force decreases. And that should make sense because you're essentially lifting the wagon up, that upward applied force. As theta increases from 30 to 60, you're going to get a greater value there, which is going to decrease the force of friction, okay? So if you were to look at some of those numbers here, force normal 100 and FTY, FTX, you would get 50 and 87 respectively. Question 19. A traffic light is suspended by two cables as shown in this diagram. Cable 1 has a force of tension of 49 newtons. So I'm going to write that down right here, 49 newtons. Okay, that's the resultant force. That's the hypotenuse of the triangle here. And cable 2 has an 85, okay, Newton resultant vector. That's that force of tension, the hypotenuse. Okay, and its theta is equal to 60 degrees. Find the mass of the traffic light. What would the force of tension be if the cables were repositioned to hang at 90 degrees? Sometimes these problems can be a little daunting, so what do we always do? Free body diagrams, we sum the forces and we get a plan of how we're going to move forward. So here is the free body diagram, and it already has force of tension 1 and 2 resolved into their components. So notice we have 2 vertical upward, and that would be the force of tension 1 vertically and force of tension 2 vertically. The downward force is the force of gravity. We also have a horizontal force of tension for both the tension 1 and tension 2. And those have been shown on the free body diagram, one acting to the left, one acting to the right. Okay? Now, summing the forces here, horizontally first, calling right positive, left negative, we have the force of tension horizontally 2 minus the force of tension horizontally 1 is equal to mass times the acceleration horizontally. However, there is no horizontal acceleration and therefore no net external force. Thus, the force of tension in the x for 1 is equal to the force of tension in the x for 2. We're going to stop there, move on to our vertical piece. We have 2 acting up and 1 force down. So let's look what that looks like mathematically. We have force of tension 1 plus force of tension 2 minus the force of gravity is equal to the mass and the acceleration vertically. However, the light is not accelerating vertically, and thus there is no net external force. Therefore, force of tension 1 in the vertical plus force of tension 2 in the vertical equals the force of gravity. So after all that, we've summed up our x and y's, and maybe now we can look at trying to find a solution here. Now, let's go ahead and pop in our trig, okay? So when you do that here, you're going to have for the force of tension 2, 60 degrees, and we have 1 being 30 degrees, okay? And you know that because you are given these angles, and these are alternate interior angles, so you're able to use that as your theta here as well. Okay, so take a look at that. Make sure you're good with that. Let's pop in our trig. Remember, T2 was that 85 Newton resultant force, cosine 60, and T1 was that 49 Newton force, cosine 30. Okay, so when we're looking at the horizontal, you can see you're going to be using cosine because these are the adjacent sides of that triangle. All right. Same with vertical. We're looking at the opposite of the angles, theta 1 theta 2. So the sine function works in this case, and we're able to get put the trig in there. Now we can actually look at finding a solution here for the mass, because we know the resultant vectors are 85 newtons and 49 newtons. We have our trig, we have it resolved. We know the acceleration due to gravity is 10 meters per second, which means we can rearrange this and solve for the mass being equal to 10 kilograms. Okay, now part B, what would happen to the force of tension if these cables were repositioned to hang at 90 degrees? All right, using a semi-quantitative approach with numbers here, you can see that the force of tension 1 and the force of tension 2, they would each hold exactly half of the force, which is 100 newtons when we look at 10 kilograms multiplied by 10 meters per second. So each rope is now holding exactly 1/2 of that weight, and you can see that here when we plug in numbers and use the trigonometry. Question 20. 3 students are pulling on a bag of Skittles. Each is pulling with a horizontal force, okay? And we went over that a few questions ago about a northward horizontal versus southward horizontal. It's still in the x direction. If a student 1 pulls eastward at 170 newtons, student 2 southward at 100 newtons, and student 3 200 newtons, but at an angle of 20 degrees west of north. So there's those cardinal directions, west of north. What is the net force caused by the 3 students on that bag of Skittles? All right, let's see what we know. All right, this one warrants a sketch because we have some vector addition going on here. All right, so we have a bag of Skittles, and we have these 3 forces acting on that one object. Okay, now let's look at this with the Cartesian plane here so we can get more of a visual. So here we have that force, and this being the 200 Newton force that is acting at a 20 degrees, okay, 20 degree angle west of north, okay, west of north. So if you're still not used to the cardinal directions, just go around and look at different positions. But this one here, we have our our positive y-axis, which we could call north. This direction here is west, and this resultant vector is 20 degrees west of north. Okay, so let's do some tip-to-tail vector addition. And the 200 Newton force will need to be resolved into its x and y components, or in this case, into its west, east, north, south components. Let's look at free body diagram here. You know, we have our 3 students here. We're showing that student 3 has this force applied, a northward component, but also has a westward component. And then students 1 and 2 have either an eastward or a southward component. So we have this laid out. So now what I'm going to do is I'm going to take these and I'm going to do some tip-to-tail vector addition so we can try to get an overall resultant vector for the net external force. Couple different ways you can do it, but it's all tip-to-tail vector addition, and both of these ways work out fine. So pause the video and think about what you're looking at here. And again, we're looking at this blue arrow, which is our resultant vector, and it is going to be the net external force. So that's what we are interested in finding out. Let's sum the forces. In the x direction, calling to the east positive and west negative. We have force applied 1 minus the force westward applied by student 3. And so we have values for this, 170 newtons minus 200 newtons. And if we look at the sign here, let me draw this on our Cartesian plane here. This is what we're interested in for the westward vector, and it is opposite of our angle theta, which we know to be 20 degrees. That's where we're using a sine function in this case. And the answer, 101.6 newtons east in the east and west, or horizontal x, okay? Now, for the y, which again is horizontal, but it is acting northward or southward. So a little weird here, the terminology. We have the northward component of student 3, and we are subtracting the southward component of student 2, and we're going to use cosine to resolve the 200 Newton resultant vector of student 3 into the y component only, and then we're going to subtract the 100 Newton force for student 2 exerts southward to get an overall answer of 87.9 newtons north. So, lining these directions up, tip to tail, we have our vectors and our resultant. We will get that the angle here in this case, because we may have our magnitude, but we also need direction. So in this case, we have the angle phi, and we can use Pythagorean theorem to find the magnitude of the resultant vector at 134 newtons. And now we're going to use an inverse trig function. Tangent to find our unknown angle phi is equal to 41 degrees. We're almost done. Last piece would be to use our cardinal directions to say the answer is 134 newtons at 41 degrees north of east. All right, and that is the net external force on this poor bag of Skittles. Question 21. You slide a 300-gram wooden block across the bench top and record velocity as a function of time. From these data, you draw a best fit linear regression. The graph of its velocity as a function of time is shown here. A. What is the magnitude of the force of friction between the block and the bench top? B. What other information can you gather from this graph here? Okay, so to start off with, just take a minute and look at where we're at. Okay, so we're in quadrant 4 of the Cartesian plane. All right, we are beneath the positive x-axis, and this is velocity as a function of time, and we are also given the equation for this best fit line, y equals mx plus b. Okay, so first things first, what do we know? Well, if we are in the quadrant 4 on a velocity time graph, if we are beneath the positive x-axis, this object is moving backwards, moving to the left, however you want to, whatever you're calling backwards. This object is moving backwards, all right? We also know over time, this object is slowing. So it's moving backwards, but it's slowing down, okay? Moving backwards, slowing down. What would cause it to slow down? If it's moving to the left, then an acceleration to the right must be exerting a net. There must be an external net force causing the object to decelerate. Okay? All right. We know we can look at the slope here, and the slope will give us the acceleration. All right? So let's go ahead and look at a free body diagram for this scenario here. This wooden block will have vertically force normal minus the force of gravity, which are going to be equal in magnitude, opposite in direction, because the block is not accelerating vertically. We also have this force acting to the right, okay? The force of friction is leading to a deceleration, a negative acceleration, all right, which is why we have an object moving backwards but slowing down, okay? All right. So summing the forces here, we have in the vertical direction, we have force normal is equal to the force of gravity. So we can actually plug in some values here and look at that because we know the mass in kilograms is 0.3. We know the acceleration due to gravity. So we know force normal is equal to 3 newtons, all right? Moving forward with this information, we can then look at the x direction, okay? And because the block is moving, we're going to denote that as the force of kinetic friction, all right? The friction when an object is in motion compared to static friction when it is not in motion. We know that the force of friction opposes the direction of the motion, which, looking at the free body diagram again, we know the object is moving backwards to the left, and force of friction is opposing that. It is moving forward, or it is in the direction forward or to the right, okay? So now what we can do is we can look at our x direction and we can say, all right, we have a value here for the mass of the block. Where did this come from? It comes from right here. Y equals mx plus b. What is the slope equal to on a velocity as a function of time graph? Well, we just said that, the acceleration. So the acceleration is equal to 0.80 meters per second squared. That's where this comes from, which means we can solve for the force of kinetic friction equal to 0.24 newtons to the right. All right. What other information can we get from this graph? Well, it turns out we can do all kinds of fun stuff here. Let's look at that. So we can calculate mu. We can find the coefficient of friction for the bench top by dividing the force of friction by force normal using the physics is fun equation. So we can find mu to be equal to 0.08. Remember, there are no units for mu, for the coefficient of friction. Okay, so now we know the coefficient of friction for the bench top. We've already conceptualized and discussed the fact that that negative velocity, it's moving from right to left, and that positive slope means that the magnitude of the velocity is decreasing, so the acceleration is positive or to the right. We talked about that one already. What about the area under the graph? Okay, that represents the change in position or displacement. So you can actually go through and find the area under the graph here. All right, you can go through, and I've done that. I want you to do it and see if you get about the same answer here of a negative 2.35 meters, which means, again, negative displacement means its change in position is to the left. Let's draw some position time graphs. Let's draw a position as a function of time and acceleration as a function of time. Okay, let's see what those look like. Here we have the position or change in position as a function of time, and here we have the acceleration as a function of time. Notice the acceleration is positive and constant at a positive 0.7991, and in the problem we actually use the value 0.80 for the acceleration in our force summation. What else? Look at this. We can use UAM equations. What fun! And we can solve for time. All right, so we can then label time on the axis here at 1.88 seconds. We can further use UAM to support the fact that this is the area under. So we can use the area under and UAM, and we get the exact same answer. So cool. So it's amazing what we can do just from that one graph of information. Okay. Calculating time, and again, we're looking at the displacement using a UAM, and it's the exact same as the area under. Very cool. Final note here that the starting point on the position as a function of time graph is at the origin, because we don't know the position relative to the velocity time graph. Problems will either tell you that starting position equals 0, but we don't know. So we went ahead and just started at the origin because we didn't know. And the curvature of the line is at a rate that decreases over time, okay, which indicates a decreasing velocity. So if you were to draw your series of tangents, slope decreases, 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 but we never see a slope equal 0 because the block never stops in the original graph, so we don't know what happens. Question 22. Draw a free body diagram for a book with a mass of 3 kilograms resting on a table. Sum the forces to find force normal. Explain why the force of gravity and the force normal are not a Newton's third law force pair. This is so important. I have my a whole question dedicated to this, all right? Which means it likes to come up from time to time on the AP exam. Here's our free body diagram, equal in magnitude, opposite in direction. Okay? This is very common, this misconception that force normal is an upward force of the table on the book. Okay? So the action-reaction force pair, the Newton's third law force pair, would be the downward force of the book on the table and not the force of gravity. Okay, think about that. So the table exerts an upward force on the book exerts a downward force perpendicular, and that is on the table. Those are the Newton's third law force pairs. Okay? The force of gravity is the downward force of the earth on the book. So the third law force pair in that case would be the upward force of the book on the earth, not force normal. Okay? So here's another example to help you with that. A bird flying. Okay, and there's a problem coming up where we're looking at some insects that are flying in a jar. Consider this motion here. So a bird is using its wings, and the wings push air down. So if the wings have a downward force on the air, then the air exerts an upward force on the wings of the bird. Okay? That is another example of a Newton's third law force pair. The air is pushing the bird upwards. Okay? The bird is pushing the air downwards. Question 23. A man with a mass M stands on a scale in an elevator. I love elevator problems. If the scale reading is equal to the force of gravity when the elevator is at rest, what is the scale reading while the elevator is accelerating down with a magnitude of a sub y? You're not asked for numbers. You're only asked to answer this in terms of variables: mass, acceleration vertically, and the acceleration due to gravity, or little g. Okay, so free body diagram first. What is the apparent weight? That is force normal. So force normal is going to be measured by the scale and give that apparent weight. Mass gravity, that's not changing. Okay, that's down toward the earth, and it is the product of the mass multiplied by the acceleration due to gravity. Okay, but notice on this free body diagram, the force normal is drawn smaller than the weight or the mass times the gravity. Think about riding in an elevator and you're accelerating downward. You feel lighter. Your apparent weight is less. Force normal is less. So remember this, guys, that the normal force is a force of the scale upward on the man. Okay? So when the elevator is not accelerating, force normal is equal in magnitude, opposite of direction for the force of gravity. So that would be when the elevator is at rest or when it has a constant velocity. Okay. In this case, the elevator is accelerating downward. So the elevator has an acceleration down, which is in the same direction as the acceleration due to gravity. When you sum the forces, let's go ahead and do that. Vertically, force normal. If we call up positive and down negative, this is where we get into that, where sometimes we won't do that as long as we're consistent. But force normal up minus force of gravity, which is down, is equal to mass multiplied by the acceleration in the y. Okay, now the acceleration is downward, which is why you see a negative a sub y. Okay, we could also choose our direction of acceleration and call that positive, in which case force normal would be subtracted from the force of gravity. But for now, this example, you can use it either way, and that's the whole point, is to show you, as long as you're consistent. So force normal in this case, if we add mass gravity to both sides, we get this expression. If we factor out mass, we get that force normal is equal to the mass multiplied by the acceleration due to gravity minus the acceleration of the elevator. So we're subtracting something. If this is 10 and we are subtracting 2, let's say, if it's accelerating 2 meters per second down, then we're getting a smaller number, 8. And so force normal is less than. Guys, think about it. Seriously, if you are in an elevator or anything and you are in free fall, it's weightless, right? You are accelerating down toward Earth at such a high rate that you feel weightless. You're in free fall, okay? So that would be where we would have here 10 minus 10 equals 0. Therefore, mass times 0 equals 0, and force normal, or apparent weight, equals 0. You look down at the scale, it says 0, okay? So here's a series of free body diagrams, different scenarios here. Definitely copy these down if you haven't already in class. So when we look at it, you are subtracting the acceleration of the system. Now the system would be the elevator, the man, the scale, the cable, whatever else we define as a system. We're subtracting that from the acceleration due to gravity. Therefore, the apparent weight goes down, and in the extreme case became 0 if the acceleration of the system was 10 meters per second down. Then we would get force normal equals 0. Okay, so let's look at these left to right here. Constant velocity. This free body diagram is the exact same as a 0 movement. So either constant acceleration or just stationary, not moving up, not moving down. Okay, so velocity equals 0. Doesn't matter. There's no net external force, and therefore no acceleration of the system. On the second one here, this is, we're accelerating downward, okay? So accelerating downward, we can look, or excuse me, wow. Accelerating upward. I apologize, class. Downward was what we did in this problem, which looks like this. But when we're going up, we're actually adding these terms together. And we'll look at this in class. No worries. We'll look at this in class. So it's the opposite. And think about it. If you're in an elevator accelerating upward, you have that moment where you feel, oh, I feel a little heavier. Okay? So really, anytime we have an upwards acceleration, you feel a little heavier. This also occurs when an elevator is going down but stopping. So you're on the 4th floor and you are arriving at the 1st floor, you feel that moment where it's heavy. Well, that's because you have an acceleration upward, which is stopping your downward motion. I like talking about elevators, in case you haven't noticed. Speaking of elevators, question 24. A person is standing on a scale in an elevator, and the scale reads 600 newtons. All right, so what's the mass of this guy? You said it, 60 kilograms. When the person is riding upward at I better underline this, constant velocity of 4 meters per second. Who really cares about that? All we care about, constant velocity. Well, that means there's no net external force on the system. So what is the scale reading when the elevator is at rest? Free body diagram. Notice the magnitudes of those two forces are equal. Of course, they are also opposite. There's no net external force and therefore no acceleration of the system. So it's the exact same. It is identical. Force normal equals mass times gravity. So we're going to have 600 newtons, regardless of if it's a constant velocity of 4 or 8 or 10 meters per second. It's the same if it were at rest. Those values are identical. And here, I just I went over this just on the last question here, where we had the scale. It says 0. Why? Because this scenario is showing free fall. Okay? And you can see anytime we have the acceleration vector going upward, what do you notice about it? Well, the scale, the apparent weight or force normal is 1,000 versus 700. Okay? So anyways, take a moment and look at that. Pause the video. I'm going to be moving on here to question 25. So we have identical fireflies. They are placed in jars in 3 different configurations. As you can see, we have 3 fireflies in A. They're hovering. In B, 1 is hovering. In C, that firefly is sitting at rest on the bottom of the jar. The jars are closed. They are put on a scale and measured. And it's asking you to rank. This is a ranking task. The weight of each jar according to the scale reading from the heaviest to the lightest. Okay. Now, a couple questions ago, I went over Newton's third law of force pair for a bird flying. And we talked about the force of the air on the wings and the force of the wings on the air. It's the same thing here. If we were to look at these, it wouldn't matter if they're flying or if they're just sitting at the bottom. It's the same weight. It's the same because of that Newton's third law of force pair. All right? Air is pushing down and it's equal to the force of the air pushing them up, allowing them to hover. Okay? And that air is pushing down on the bottom of the jar. Okay? So if we look at these, we're going to see that the only factor that's going to determine the weight is the number of fireflies in the jar, where A is greater than B is equal to C. So B and C are the same. It doesn't matter whether in C the firefly is just hanging out at the bottom or B if the firefly is actually hovering in the jar, you're going to have the exact same reading on that scale. Question 26. All right, another elevator. The figures below depict situations where a person is standing on a scale in 8 identical elevators. Each person has a weight of 600 newtons, so their mass is 60 kilograms, and elevators are stationary. Now the elevators move or accelerate according to A through H. Rank the figures from greatest to least on the basis of the scale weight. The scale weight is force normal. That is the apparent weight. So if you look through each of these scenarios, you're told the current velocity and you're told the acceleration. Okay? So from greatest to least, and I'll briefly explain why. Force normal, that's what we're looking at. We have A and E are the greatest. Okay, so A and E. What's happening here? Well, in A and E, there's an upwards acceleration. And what did we talk about A and E when it's accelerating up? That you're actually adding the acceleration of the system to the acceleration due to gravity. Every time you're adding them. Sum the forces and prove it to yourself if the last several problems haven't explained it to you, or come ask me in class and I'll go through this summation again. But you're always going to end up with the acceleration of the system plus the acceleration due to gravity, which means force normal is going to increase. All right, so A and E, we have an upward acceleration. Notice very little concern over that velocity. All we care about is there's an upward acceleration. Okay, all right, the next one here. The next one here. We have C, D, and F. All right, C, D, and F are the next from greatest to least. And so what's occurring on all of these? Well, we have zero acceleration, all right? Sure, we have these velocities, 0 and 6 and 3, but who cares, okay? If there's no acceleration, there's no net external force, so the scale readings are going to be equal to mass times gravity. Those will be the same. Then we have B. So let's look. What's different about B? And we might as well also look at G and H while we're at it. G, H, because those are the last three. B, we have a downward acceleration, all right, of 2 meters per second. And anytime the acceleration is downward, as we've shown repeatedly, you're subtracting that acceleration of the system from the acceleration due to gravity. So force normal is less than what it would be for an object that was stationary or moving with a constant velocity. The reason G and H are greater than B is because the magnitude of the acceleration is greater. In fact, these are both at free fall, okay? So these are both experiencing weightlessness. Now, I want you to ask yourself, okay, but there's a velocity upward. How could that occur? And then I want you to come explain H to me in class. I want to know a scenario, story time for H. How is there an upward velocity yet a downward acceleration that is equal to the acceleration due to gravity? Question 27. 4 blocks of masses 20, 30, 40, and 50 kilogram are stacked on top of one another, and they're in an elevator, okay? I love this. The elevator is moving downward with an acceleration. So immediately, I really hope immediately you're thinking, oh, okay, it's moving downward. So regardless of what I'm doing for my summation, I'm going to end up with the mass of whatever I will have G minus that acceleration. So the apparent weight or force normal or contact force, whatever verbiage is being used, is going to be less than what it normally would be. Okay? So we are concerned with this contact force here between the 30 and the kilogram. So that would be the normal force here. And if you look above the 40, we have two. Guys, you can let me see if you can essentially consider this one object. And you can conceptualize this as one object that is 50 kilograms, okay? Or 500 newtons for that downward force, contact force it's exerting on this 40 kilogram box, okay? So our free body diagram, we have mass gravity, and we have the force normal is less magnitude than mass gravity. Why? Right here's the answer. The system's accelerating downward. So we're going to have an apparent weight less than expected. Okay? We've already gone through the intuition here. Now let's sum these forces up. Okay, so if we call up positive and down negative, in the vertical, we end up with force normal minus mass gravity equals the mass multiplied by negative acceleration. Okay, now in class, you've probably heard me tell you, hey, if the downward direction, you can call that positive. So call the overall direction of the acceleration of the system positive. In this case, we're calling down positive and up negative. But you've heard me say in class, either way works. So in this case here, I'm sticking with the convention, up is positive, down is negative, which means I need to carry this signage here and have a negative acceleration for the system. So when I solve for force normal, which is the contact force, and I factor out the mass, which is 30 plus 20, I get that I am subtracting, just as I said here at the beginning of this problem, the acceleration of the system from the acceleration due to gravity, which means I'm getting 10 minus 3.2, which means force normal is not what we would expect. If it were in equilibrium, it would be 500 newtons. But this system is experiencing a net external force, and therefore we have a force normal that is less than expected, just as we drew on our free body diagram. Okay, again, if this were moving at a constant velocity, or if this were at rest, i.e. stationary, then the force normal would be 500 newtons, but it's less than that because it's accelerating downward. Okay. Question 28. Calculate the coefficient of friction, mu, for the data graphed in question 21. So you're going back to question 21, and if you've already viewed question 21, you should be good with this idea of how to calculate, calculating mu using the physics is fun equation. All right, rearranging for mu, force of friction divided by force normal. If you haven't, go back and rewind this and check out 21, where we talk about what else can we find from this graph. One of those things that I discussed then was actually that we could find mu, and mu is equal to 0.08. So that was the coefficient of friction for the surface of the bench in that particular problem. Question 29. This diagram it shows a block. It's sliding down an incline at an angle theta. So a diagram below shows a block. I'm going to do a downward and put V here, okay? So I remember it's moving down. What can be concluded about the coefficient of kinetic friction? That's that friction of motion as opposed to static friction between the bottom surface of the block and the surface of the incline. So we're asked about right here. And if this box is sliding down the incline, we know kinetic friction is opposing that motion and therefore is up and parallel to the incline. All right, so let's start with our free body diagrams. Notice that we are looking at the perpendicular and parallel components as opposed to the horizontal and vertical, because this is relative to the angle of inclination for this object. So our free body diagram for the forces acting perpendicularly is that force normal and the force of gravity perpendicular are equal in magnitude, opposite in direction. For parallel, we have the force of gravity parallel, which is the driving force for the object down in parallel, but it's being opposed by the kinetic friction, which is up in parallel to the incline. Okay, so I've shown you this in class. If we were to resolve the force of gravity, and you would never do a free body diagram, I want to make this clear, with resolved and unresolved forces on it. You draw the free body diagram once with unresolved forces, then you would draw the free body diagram again, resolving any components or resolving any forces into their either x and y or perpendicular and parallel components. So if you do not have this copied down, you need to write this down now so you understand. For the purpose of illustrating this only, this diagram has the unresolved and resolved components. Again, you would never include both of those on one free body diagram. So let's look at this here. We have angle theta, and we've used this angle theta, and a lot of students get confused about, why we're using sine theta for parallel and cosine theta when it's perpendicular. Okay, let me show you something here. This angle theta is this angle theta. You can play around with the geometry and show that, looking at 90-degree angles and making sure everything adds up for the triangle as far as the degrees. But so this vector here is this. Okay, so if I were to move this down here, it's the same. It's the same angle and the same length or magnitude. So that is why if you are finding the force of gravity parallel, it is equal to the opposite. So whatever your mg is, and it's equal to the opposite, sine theta. I wanted to show you that. Along that same line of reasoning, the adjacent side of this triangle is cosine. Okay, and that's going to give you the force of gravity perpendicular. All right, so mass times gravity times cosine theta is going to give you the force of gravity perpendicular. All right, so let's look at that in our summation of forces here. We have our perpendicular direction. So if we call up positive, then we, up and perpendicular, which is force normal, then we would call the opposite direction negative. We get an equal, this equals 0, however, the object is not accelerating in these directions. So those are equal to 0, which means force normal is equal to mass gravity cosine theta. All right. Compare that to the force normal of an object on a horizontal surface that is in equilibrium. Looking at the parallel, okay, so the force of gravity parallel, which is that driving force down in parallel for the ramp, minus that opposing force of friction equals mass acceleration parallel, okay? So we can also use this in this particular question. Indeed, we're being asked about the coefficient of kinetic friction. Using the physics is fun equation, we can rearrange this to find some really cool stuff. We can use force of friction is equal to mu multiplied by force gravity, or mass times gravity. And cosine theta, students tend to forget the cosine theta. Don't forget it. I just went through the intuition here of the angles and how these forces work out for an object on an incline. Okay, so if we look at force normal, we already have a summation. So, don't worry about numbers here. But what you do want to worry about is making sure you have your summed forces, and then because you have two overall equations, you can rearrange one in terms of another, which means you can plug that information into the other equation to solve for a variable. Okay, so in this case here, force of friction is directly proportional to mu. Okay, and hopefully you can see that here. That's always going to be the case, in fact. As mu goes up, force of friction goes up. As mu goes down, force of friction goes down. Okay, and it's also going to be directly proportional to the force of gravity. So as mass goes up, force of friction would go up by way of increasing force normal. All right. Mu does not change unless the surface changes. So it is a property of the surface. So if you're working on a problem about a sled going down, say, a snow slope, and then all of a sudden the sled encounters a very rocky patch, and the mu would then change. But for mu on the surface of the bench tops, say at school, mu's not going to change. But force of friction can be manipulated, as we've probably already done in lab. So theta does not have an effect on the value of mu. However, as theta increases, the force of friction decreases, as cosine 90 is 0. And we talked about this a little bit. We gave in an example of a wagon, where we said what would happen if the angle of inclination went from 30 degrees to 60 degrees, or increased. So go back and look at that problem as well. And we can certainly look at this more in class if you would like, but you should have enough information here to make up numbers, use these equations, and prove it to yourself. But you do know cosine 90 is 0, so as that theta increases, we're getting smaller. Question 30. The diagram below, we have a 4 kilogram object, and it's accelerating 10 meters per second, and it's accelerating to the right. And we see indeed a force applied of 50 newtons acting to the right. The magnitude of the frictional force is what we're trying to find here, and we're also trying to find the mass of the block. What mass of a block would it have to be for there to be no net external force? So, two parts to this problem. Part 1, what is the magnitude of the frictional force? Part B, how much mass would this block need to have a 0 net force? Which means it would either be at rest or at a constant velocity. We're going to start with a free body diagram. We are showing here the force applied is greater in magnitude, acting horizontally, and it's greater than the force of friction. However, force of friction is opposing the motion, which we are told it's accelerating to the right. And we see force normal equal in magnitude, opposite of direction for the weight, or mass times gravity. Okay? Summing the forces here vertically first, we get force normal, which we'll call up, minus mass gravity equals the acceleration vertically, which there is no acceleration vertically, it's only horizontally. Therefore, force normal is equal to mass times the acceleration due to gravity, or 40 newtons in this case. Now let's look at the horizontal summation. Calling right positive, left negative. The force applied minus the force of kinetic friction, because it's moving, is equal to the mass multiplied by the acceleration of the object horizontally. and it is accelerating at 10 meters per second. So we can actually plug in values, rearrange, and solve for the force of kinetic friction to be 10 newtons. So that is the magnitude of force, but the force of friction overall is 10 newtons to the left, or a negative 10 newtons. Okay, for part 2, for the block to experience no net external force, we would need the force of friction to be 50 newtons to the left, right? So there's a force applied of 50 to the right. It's moving to the right with a force of friction of only 10 newtons, but we want the a vector that is equal in magnitude, opposite in direction. So in other words, we need force of friction to be equal to 50 newtons to the left, okay? So as you've learned, or you're learning, we're always going to keep the physics and fun. Is fun equation ready, accessible? In this case here, we can show that force normal, which we know to be equal to mass times gravity, and we also know that the force of friction is equal to mu times force normal. So as force normal goes up, force of friction goes up. Well, as the mass of the object increases, the force normal increases, and the acceleration due to gravity, little g, stays the same. So if we were to look at force normal is equal to 4 kilograms multiplied by 10, we get 40 newtons. All right. And if we were then able to take this information, we could find the coefficient of kinetic friction is equal to 0.25. Remember, that's dimensionless. All right. So force of friction is equal to mu force normal. Look, force normal. Well, we know from our vertical summation that force normal is equal to mass times gravity. So we can take what we know about force normal, which we know quite a bit about, it's 40 newtons, and we can plug it in here. And since we know mu, let me erase that right there. We can plug in 0.25 multiplied by the mass, multiplied by 10. That's equal to 50 newtons. We want it to equal 50 newtons. If it equals 50 newtons to the left, then this object will be put into equilibrium, okay? i.e. no net external force. Solving for the mass, we get 20 kilograms. Remember, we can't change mu. It's a property of the surface, okay? But what can be manipulated, and what you will be doing in lab, if we haven't already, is manipulating the mass. By manipulating the mass, you're increasing force normal. By increasing force normal, you're increasing the force of friction by way of increasing force normal. Okay? All right, very good. So answer there, if this block were 20 kilograms, there would be no net external force on the block, which means no change in its state of motion, which means no change in velocity, which means no acceleration. Moving on. All right. Is the object still moving? Well, I just went over that with you. Okay. It could be, but regardless, it has a constant velocity. Okay. So it's probably still moving, just at a constant velocity. All right. Moving on. Question 31. All right. A 7 Newton block is on a rough surface. So mu is substantial. It is being pulled by a force F1 at an angle of 30 above the horizontal. The block is initially moving to the right. Okay, I'm going to show that here. I want to show that. There's a V naught, and it's to the right, 5 meters per second. That way I know it's moving to the right. The coefficient is 0.20. A, is it possible for the block to be slowing down? If so, give a possible value for the magnitude of the force that would allow the block to be slowing down. If not, explain why with reference to our summation of Newton's second law. Let's start with A, because there's quite a bit there to look at. Our free body diagrams for this particular scenario We have the angle theta, which means we're going to be resolving into the x and y components using trig. We'll use sine for vertical, cosine for the horizontal. When we do our free body diagrams, we have our component vector or force resolved. So we're showing force normal up, positive. We're showing the force of 1 that is vertical, force 1y up, positive, mass gravity down and negative. We're showing to the right positive. Well, there's a force exerted in the horizontal direction, and that was the force that we'll use the cosine function to determine. And there's a force of kinetic friction, and a force of friction is always opposing the motion. So, and we know this object's moving to the right, therefore force of kinetic friction must be to the left. So, the overall idea here is if the frictional force is greater than, so if the force of friction is greater than the force in the horizontal, the block could be decelerating or slowing down. So yes, it's very possible that there could be a net force to the left, all right? All we've shown here is if force of friction is greater than that force to the right, which again is not the entire force 1. It's force 1 multiplied by cosine theta to give us that x direction. So let's sum the forces and actually look at this. If we look at our vertical component first, force of normal plus the vertical force, which we'll get using sine, is equal to mass gravity. Mass gravity in this case is 7 newtons, okay? Or 0.7 kilograms multiplied by the acceleration due to gravity, 10 meters per second. That's where that comes from. In the x direction, calling right positive, left negative, so the horizontal component of the force minus the force of kinetic friction equals mass times the acceleration in the horizontal. Now, we can now pop in our trig, and we're going to use cosine, as I've mentioned repeatedly already, equals mass times that acceleration. Now, physics is fun. Always keep that one ready when we're doing these types of problems. So we have the force of kinetic friction equals mu multiplied by force normal. Okay? We also know that force normal plus force 1 in the y direction is mass gravity. All right, which means force normal is equal to the mass gravity minus that vertical component. All right, and so if we know force normal is equal to this, then we can plug that in right here and find information about the force of kinetic friction. Okay? So you can see that being done here. Okay, now it's time to make up some data and make up some numbers and employ a semi-quantitative approach to this problem. We're answering it with a mixture of conceptualization and words, but also with mathematics and numbers here as well to support our answer. Okay, so again, this entire piece here, shaded in yellow, represents the force of kinetic friction. Okay, so remember, we need this force to be greater than the x horizontal force. Okay, so let's make up some numbers here. Let's go ahead and put 2 newtons in for the force. The overall resultant force is 2 newtons. All right, so 2 multiplied cosine 30, which is 1/2, which is 1, minus our value for mu, 0.2, multiplied by the 7 newtons, subtracting the value we made up in red, 2 newtons, just going for it, just throwing a number in there. Sine 30 equals mass times the acceleration in the x. We simplify that, we get 1.7 newtons minus 1.2 newtons. So what does that tell us? 1.7 newtons is still greater. That's greater than 1.2 newtons. So this number isn't going to quite cut it here. All right? We need a different number here. So this will not work. That's okay. Let's make up another number and go ahead and put it in. Let's now call F1 equal to 1 Newton and plug in that value. So we've gone from 2, now we're decreasing it all the way to 1. And we're plugging in our values, and we have mu and 7 newtons. Again, that we're told this in the problem. We made this number up, and we're going to go ahead and solve for this piece here. And what do we see? We see that our overall force of kinetic friction is now 1.3, which means it is greater than the x word force applied, which greater than. So the force to the right of 0.87 newtons is less than the force to the left, which means this block will be decelerating. It will experience a net external force by the force of kinetic friction to the left. Okay, and the last piece here, we're asked in B, in order to double the block's initial velocity, V naught, from 5 to 10, how must the magnitude of force 1 change? Okay, and that, I hope that question feels a little off to you, because the net force is related to the change in velocity or the acceleration, and not the object's speed. Okay, so we cannot answer part B because Newton's second law states that the sum of forces, okay, is equal to the mass multiplied by the acceleration. And we can't simply answer this question. So just to make a point on that one. Question 32. A horizontal tension force of 8 newtons is used to pull a 20 newton wooden block or box moving toward the right along a horizontal wood surface. Okay. The coefficient of kinetic friction for wood is given as 0.3. That's our mu value. Calculate the magnitude, I'm going to go ahead and underline, of the frictional force of the box. Okay, let's just start with that. Start with our usual free body diagram. Force normal equal and opposite to the weight or the force of gravity, or the mass multiplied by the acceleration due to gravity. And we have a rightward force applied of 8 newtons. And we are told that this box is moving to the right. Okay, so we're going to assume there's a net external force to the right, and so on the free body diagram, that's been drawn slightly larger than the opposing force of kinetic friction. Summing the forces here, you see vertically that we end up with something that's quite common for an object on a horizontal surface. Force normal is equal and opposite to mass gravity, so we can actually calculate force normal, all right, as 20 newtons. And in the x direction, calling right positive, left negative, force applied minus the force of kinetic friction is equal to the mass times the acceleration horizontally. Now, physics is fun time. Using the physics is fun equation, you can actually calculate the force of kinetic friction because you are given mu is equal to 0.3 multiplied by the 20 Newton force that you found through summing in the vertical direction, gives you an overall force of kinetic friction of 6 newtons. Part B, you are asked, identify Newton's third law of force pairs acting here. Okay, so the rope is pulling the box to the right, Okay, so it's exerting a force to the box on the right. Box is exerting a force on the rope to the left. All right. The wood surface is exerting a frictional force on the box to the left. And the block or box is exerting a frictional force or an equal and opposite force on the wood surface to the right. A lot of students never think about that. What is the force of friction? Well, there must be a Newton's third law of force pair. So if the wood is exerting a leftward force, then the box is exerting a rightward force on the wood table. Okay, and then of course we have the box is exerting a force down on the table, and the table is exerting an upward force on the box. And we call that force that the wood exerts upward and perpendicular on the box force normal. Next part of this question, determine the magnitude, once again, underline just in case, of the force acting on the box. All right, so let's go ahead and use our summation horizontally. And we're going to do 8 newtons to the right minus the 6 newtons we calculated in part A. And we know the mass of this object is 20 newtons, and we've divided that by 10 meters per second, which gives us 2 kilograms. And we are able to find that net force as 2 newtons. So there is indeed a net external force on this system. Part D, calculate the magnitude of the acceleration on the box. So now we can simply use this equation and the fact that we know what the force is, and we can find the acceleration of the box is 1.0 meters per second. Question 33. A 10 kilogram wooden box sits on a wood surface. The coefficient of static friction between the surfaces is 0.42. Remember, that is dimensionless. A horizontal force of 20 newtons is applied to the box. What is the force of friction on the box? Well, we need free body diagrams. We need to sum the forces. We need to be able to understand what's going on here. So our free body diagram to start with, we've summed the forces. And I want you to please note you were given the static friction, okay, which will match the force applied in this case until the object moves. All right. And we've talked about that in class as well. I've given the example of me applying a force on the table, okay, and the force of static friction matching that force until it is overcome, until we see that maximum peak on our graph that we've looked at, the force of static friction maximum followed by that drop where the force of kinetic friction is less than that, okay? Anyways, summing forces vertically, calling up positive down negative, we end up with force normal is equal and opposite to mass times gravity, which we can solve for to find is equal to 100 newtons. So now horizontally to the right, positive, left, negative. So we can go through and solve for the force of static friction, but we need to use the physics is fun equation and mu. So you're given mu, you know you're going to use physics is fun. 0.42 multiplied by 100 equals 42 newtons for the force of static friction. So what does that tell us? The force applied is 20 newtons. Okay? This box doesn't move. The force of static friction is 42 newtons. It is in equilibrium. So even though there's a force that is being applied to this box, it won't move until over 42 newtons. So as I've already said several times, this case here, the applied force is going to match the force of friction. It's just going to have an opposite direction. So the force of friction on the box is also 20 newtons. It is not until we get more than 42 newtons that this box would accelerate, and then the static would turn into kinetic friction. Okay? Question 34. A crate of mass 100 kilograms is at rest on a floor. It's not moving, so we're given mu for static friction of 0.4. If a force of 250 newtons parallel to the floor is applied to the crate, will it move? If so, what is the coefficient of kinetic friction? If not, what is the magnitude of the force of static friction on the crate? Okay, let's start with our usual. Let's sum the forces here. Let's do our free body diagram. Here's our layout. Force applied to the right is matching the force of static friction to the left. And so that's our starting point. If we go further and sum, we get that the force normal is equal and opposite to the mass gravity, which we can solve to be 1,000 newtons in this case. Horizontally, we have right positive, left negative, so we're subtracting the force of static friction from the force applied, and that's going to equal the mass multiplied by the acceleration horizontally. Physics is fun. We have mu. You know we're going to be going there. So we can solve for the force of static friction and find that it is equal to 400 newtons. Remember what we're asked for here. Will this crate move? And if so, what is the coefficient of kinetic friction? So let's look at our horizontal movement. That's where we're going to determine if there's an acceleration or a net external force horizontally. So 250 newtons is being applied. The force of static friction is 400 newtons. So no way this box does not move, because it would require more than 400 newtons for this to accelerate to the right. Therefore, and the last part, if not, what is the magnitude of the force? The magnitude will match that force, okay? So the force of static friction will match the force applied, in this case, 250 newtons. The force applied being to the right, the force of static friction opposing that and being to the left, but their magnitude is identical. Force static friction is equal to the force applied. Their magnitude's the same. Question 35. A group of Paulding County High School magnet students want to explore the relationship between the force of static and kinetic friction across the horizontal desktop. They decided to perform a drag test by dragging a 3.24 kilogram block using a force sensor to collect data. The students decided to perform 6 trials to ensure data can be replicated. Wow, these sound like some awesome students. Their graph of force as a function of time can be seen below. Part A. Calculate the approximate coefficient of maximum static friction and calculate the coefficient of kinetic friction. Okay, so part 1, we're going to find the maximum static friction that must be overcome to set this object, in this case, to set these blocks or the block into an acceleration off to the right. So that would lead in a net external force and acceleration. Okay, so for part A, you're going to get these values from your graph here, and we're going to look at the maximum static friction first, this region here. Okay, so we have our force normal, and we are able to look at this information and take the 16 newtons from the force of friction that we have here and divide that by force normal, which is the 3.24 kilograms multiplied by 10, or the acceleration due to gravity. So we're able to get this right off the graph, and we get the mu of static friction. We get a very high coefficient of static friction maximum of 0.49. And remember, there's no units on the coefficient of kinetic and static friction. That's our maximum value before we set the object in motion. Okay, so the next piece of this would be calculating the coefficient of kinetic friction. And you can get that value again directly from the graph, all right, during this drag test. And we've either already done this in class or you will be doing this in lab. So the physics is fun equation is the same, but notice how the force is less for kinetic than it was for the maximum static, okay? So we have an 11 Newton force that was required on average, divided by the force normal, which again we get by mass times gravity, and we get a value of 0.34 for kinetic friction. Again, these all came off of the graph here that was produced. Part B, explain why the coefficient of static friction is greater than the coefficient. Well, it's much more difficult to accelerate an object and cause a change of state of motion from rest than it is to actually keep it in that motion, okay? So again, picture me in class pushing on the desk. Oh, it's so hard. And then once I get it moving, this isn't too bad now, okay? So to accelerate an object into motion from rest versus keeping it at that constant motion, it's going to require far more of a force to initially get it to move or accelerate rather. Question 35. You apply a horizontal force of 3 newtons to a book with a mass of 0.8 kilograms. The values for the coefficients of friction between the book and the incline are mu for static friction is 0.3, mu for kinetic friction is 0.25. A, does the book move? B, if so, what is the acceleration of the book? You know what we're going to do, a free body diagram. We're not exactly sure if there is a net external acceleration, so kind of a generic free body diagram to help us get started. We're going to sum the forces in the y. We're going to realize force normal is equal and opposite to the force of gravity, which means force normal is equal to 8.0 newtons. Then in the horizontal direction, calling right positive and left negative, we're going to have the force applied to the right minus the force of static friction is equal to mass times acceleration horizontally. Physics is fun, guys, so let's go ahead and use that equation because we're given mu and pop in some values. Be careful, use static friction in your equation and not kinetic. So 0.3 multiplied by that 8 Newton force, that is force normal, gives us 2.4 newtons. So the force applied was 3 newtons to the right, and the max static friction here is 2.4. So the book will move. That's great. That means we can move on to part B. Nobody would want to just skip over. How boring would that be? In part B, you have to switch. Remember, that object is now in motion. So just as we went through on the last, when we looked at that, we had the acceleration. We hit this high spot and then it dipped down, remember? Where this was the maximum static. Well, we're now in this region here, so our mu value is less than the static max. And now we're going to look at kinetic. We're going to plug in our values, switching 0.3 to 0.25. We still have the same force normal from our vertical summation, and we get 2 newtons. Okay, so now we have the fact that this net force is 2 newtons for kinetic friction, and the net applied force, the applied force to the right is 3. So 3 newtons minus 2 newtons equals the mass of the object, or 0.8 of a kilogram, multiplied by the acceleration horizontally. Solving for the acceleration horizontally, we get a positive 1.25 meters per second, or 1.25 meters per second to the right. Okay, so now we can actually redraw the free body diagram and make it accurate. Kind of a generic one at start up here, but now we can redraw it and represent this vectorially. Show the force of the force applied is greater in magnitude than the force of kinetic friction opposing that direction. Okay, question 36. A 1,200 kilogram car with anti-lock brakes is driving on the snow with an initial velocity of 15 meters per second, and it slows to a stop in 5 seconds. Wow, this screams UAM and kinematics. Determine the coefficient of friction between the tires and the snow. Okay. Determine the coefficient. Well, we better start with a free body diagram, and we're representing force normal is equal and opposite magnitude of the mass gravity, and we have a force opposing the motion. So if the vehicle is presumed driving to the right, that's the velocity is positive, then the force of kinetic friction would be opposite of that and to the left, okay? And we have a vehicle that is decelerating, and we have a delta t, change in time of 5.0 seconds. So, in its simplest form, acceleration is equal to change in velocity over change in time, and those values of taking final minus initial gives us an acceleration of negative 3.0 meters per second, or 3.0 meters per second to the left. Okay, so it's decelerating. It's the opposite direction of the velocity. All right, so now that we know the acceleration, we can apply Newton's second law and sum the forces here. Vertically, we end up with force normal is equal to mass times gravity, or 1,200 newtons, or excuse me, my goodness, 12,000 newtons. All right, and horizontally, we get the one force that is acting, the force of kinetic friction, is equal to mass times acceleration horizontally, which we just found to be a negative 3.0. So this is a plug and chug fest. We can put these values into the horizontal summation, solving for the force in the x direction to be negative 3,600 newtons, okay? So we know the force in the x direction, and that force, which is the force kinetic friction, is to the left, hence the negative sign here. So let's use physics is fun to try to find mu, or the coefficient of friction between the tires and the snow. We know everything else now, so we can simply plug in our values that we obtained from the physics is fun equation and the vertical summation, and we can plug these in and get a mu value of 0.3. Remember, that is dimensionless. Okay, so looking at this here, we can see our horizontal summations. We can see how we can actually plug in mu, where force normal equals mass times gravity, and we can cancel out the mass, all right? So you might be saying, why am I showing you this? Why is he showing us this? There is no dependence on mass. It doesn't matter that this is a 1,200 kilogram vehicle. For this situation, finding mu here, we can simply cancel the masses out, and I wanted to make sure that I was able to actually show you that, okay? Question 37. A 2.5 kilogram mass is held at rest on a frictionless 20-degree incline by a force F. What is the magnitude of F? Okay, and determine what angle of inclination would result in a net external force and thus an acceleration. Okay, all right, so this mass is just sitting on an incline, and there's a force up in parallel that's holding it there. Sounds like we better do a free body diagram. We need to do one for the perpendicular direction and the parallel direction. Next, we're going to revisit the fact, and if you have not viewed some of the earlier problems, I've gone over this intuition behind the forces and why we use the sine versus cosine for here. So if you're viewing this again, then it's just a repeat, and that's no problem at all. This theta is the same as this theta. This arrow vector, this force, is the same in magnitude and direction as this one here. So to find parallel, you're going to use the sine. To find perpendicular, you're going to use a cosine for that adjacent side there. Okay, so let us sum the forces here. Parallel, we're going to call, in this case here, the direction of the acceleration down and parallel the incline positive. So we're going to actually say that the force of gravity multiplied by the sine of theta minus this applied force is equal to the mass multiplied by the acceleration parallel. Now, this box, this object, is not accelerating in the parallel direction. It's not accelerating in the perpendicular direction either. So this, in this case, equals 0. And so we get some relationships here that we can look at. For example, force normal is equal to mass times gravity times cosine times 20 degrees. Okay? So we can look at all this information. We can plug in our trigonometry here for the parallel, and we can solve that and show that mass times gravity times the sine of theta is equal to the force, because it's not moving. Remember, it was equal to 0. Both of them were. So because of that, we're able to find the overall force, and that is equal to the mass times the acceleration due to gravity times the sine of 20 degrees, which gives us a force of 8.6 newtons. All right, that's the force, okay? Now, the next part of this is saying, so we know the magnitude of the force with this scenario. Given that force, determine the angle of inclination that would result in a net acceleration or net external force of this object down and parallel to the incline. We cannot answer this. We have calculated the magnitude of the force as 8.6 newtons. We know nothing else. Even as theta increases, we know the parallel component of the force of gravity will also increase. Yes, that makes sense. However, we do not know anything else about this force other than in this scenario, on a 20-degree angle, 8.6 newtons is required for this object to be at rest on the incline. That's all we know. So we cannot answer part B of this question because we know nothing else about this force. Question 38. A 10-kilogram box initially at rest. Okay, I'm going to slides down a frictionless 18-degree ramp. Find the acceleration of the box down the incline. Find the time it takes for the box to slide 2 meters down the ramp. Okay, so these are getting to be pretty fun here, but we're still going to do the same thing. We're going to sum our forces and look at our free body diagrams, and it looks like we might need to delve back to some UAM and some kinematics here. So we have force normal is equal and opposite in magnitude to the force of gravity perpendicular. We also have one force acting parallel to the incline. We do not have a force of friction, so the only parallel force is the parallel component of the force of gravity. Okay. Summing the forces in the parallel direction, we get that the force of gravity parallel is equal to the mass times the acceleration of this object parallel. We know from our studies and the trigonometry that I've gone over repeatedly that the force of gravity parallel is equal to the mass times the acceleration due to gravity multiplied by the sine times theta. In the perpendicular direction, we know that the force normal is equal to the mass gravity cosine theta. And obviously mass gravity being the force of gravity, and that multiplied by cosine, because that's that adjacent side of that triangle there that's perpendicular. And if you are just viewing this problem and none of the earlier ones, you might want to rewind and look at that if you don't understand where the sine and cosine theta came from for this object on an incline. Okay, so let's continue on with the force of gravity in the parallel direction, which we've shown to be equal to mass times acceleration. Then all of a sudden we see there's no dependence of mass. This is independent of the mass of the object, so who cares if it's 10 kilograms? And we've shown this a couple times so far in class and on the last problem with the vehicle. We were able to completely cancel out mass. So here mass cancels out and the force of gravity parallel is equal to the acceleration of gravity, little g, sine theta, and that's going to give us a value of 3.1 meters per second, okay? So that is the acceleration of the box. It is sliding down and parallel at 3.1 meters per second, okay? Find the acceleration of the box. Oh, we did that, and the amount of time it takes for the box to slide 2 meters down. And time is where you would that screams UAM in kinematics. So if we use this UAM equation and recognize that the box is at rest, V naught T becomes 0, and we are left with 1/2 times the acceleration, which we found to be 3.1 multiplied by time squared. And that's going to give you an overall time of 1.14 seconds is the amount of time it takes for this box to slide down 2 meters down a frictionless ramp that makes an 18-degree angle above the horizontal. Mass did not matter. Question 39. A block weighing 10 newtons is on a ramp inclined at 30 degrees to the horizontal. A 3-Newton force of friction acts on the block as it is pulled up the ramp. So friction's down the ramp at a constant velocity. I better underline that. The force applied to pull the box up the ramp acts parallel to the incline. Draw the free body diagram for this problem and determine the magnitude of the force applied. Well, we're always going to draw the free body diagram. Okay, so it is important to think about it though. The box is, this time it's moving up in parallel. So because it's moving up in parallel, the force of friction, the force of kinetic friction is down in parallel. Well, what else is down in parallel? Always the force of gravity, the parallel component of the force of gravity. And the force applied is up in parallel to the ramp. And our force is perpendicular. We have force normal, same magnitude of the force of gravity perpendicular, just opposite directions. Summing the forces here in the parallel, we are able to get our force applied minus the force of friction minus the force of gravity parallel equals mass acceleration parallel, where there is 0 acceleration parallel. How do we know that? Because we are told explicitly there is a constant velocity, there is no change in velocity, and thus there is no acceleration. Now, that allows us to simplify this and have an expression for the force applied being equal to the force of friction plus the force of gravity sine theta. In the perpendicular direction, we end with force normal being equal to the magnitude of the force of gravity perpendicular. and we can use that information there to find force normal, because we know force normal is equal to mass gravity cosine theta right here. I want to make sure I'm being clear on that, so I'm not going too fast. Force applied is equal to the force of friction plus force normal sine theta. All right, so with this information here, we can say, all right, so we are told we have a 3 Newton force of friction, so we can plug that value in. We know the force of gravity because we know the weight of the block, which is 10 newtons, and we have sine theta, and we're told that. So we're told that angle theta. So we can find the force applied, and it is equal to 8 newtons. All right, now let's look at problem 40. A 10 kilogram box is released from rest, and it slides 20 meters down a 40-degree incline. I think we're drawing a picture for this one. A frictional force of 10 newtons acts on the object. So the box is sliding down the incline, which means force of friction is up and parallel to the incline. Determine A, the acceleration of the block down the plane. B, oh, yeah, fun, the amount of time for the block to slide to the bottom of the ramp. Okay, free body diagrams, always. One for perpendicular, one for parallel. There are 2 forces acting in each one. Force normal, again, same magnitude, different opposite direction from the force of gravity perpendicular. On the parallel free body diagram, we have a force of gravity parallel that is down and parallel the incline. We have the force of kinetic friction opposing that motion, and we've drawn the force of gravity parallel larger in magnitude because the problem tells us that it's sliding down. It released from rest, 0, and it slides down, so there must have been a change in state of motion or change in velocity, i.e. an acceleration. So we know we have an acceleration, which is why we can draw that a little bit bigger. We know we're going to sum forces. So if we start in the parallel direction and we call down in parallel positive. If we call down in parallel positive, then we're calling up in parallel negative. So in this case here, we're subtracting the force of friction from the force of gravity parallel, and we're able to rearrange this information, and we are also able to take our trigonometry and put mass multiplied by little g times sine theta. We're told theta is 40, so we can then end here with this expression. That's okay. We're going to stop there. We're going to move to the perpendicular components and sum those up. Once we've done that, we find force normal is equal to mg cosine theta once again. Well, that's some good information for us, because that will allow us to take some of this and apply it to our parallel piece. So we have the mass gravity sine theta, and that was 100 newtons, okay, which is the mass of the object 10 multiplied by little g, the acceleration due to gravity. That's where the 100 newtons, that's the force times the sine, 40 degrees, minus 10 newtons, okay? And that's because we're told the frictional force is 10, so we can plug that in here. We know the mass of the object. We have all of these variables. Let's solve acceleration down in parallel to the incline of 5.4 meters per second. Remember, we've called down in parallel our positive direction, so this is a positive 5.4 meters per second. Now, you know with time, you know we're going to use UAM. We're going to use a kinematic equation. We are told from rest. From rest tells us that V naught is equal to 0, which means this whole piece here goes away. And we're left with 1/2 times our acceleration that we determined using Newton's second law multiplied by time squared. Solving for time gives us 2.7 seconds as our final answer for part B. In question 41, a box of unknown mass is released from rest and slides 20 meters down a 10-meter high frictionless incline. You are asked to determine the acceleration of the block down the incline and the amount of time it takes for the block to slide to the bottom of the incline. We'll start off with our free body diagrams, both in the perpendicular and parallel direction. We have some sort of sketch here, and notice with the information we're given, we're going to need to use an inverse trig function to find the angle theta. So in this case here, we know the opposite and we know the hypotenuse. So if we use an inverse sine function, we find theta to be equal to 30 degrees. Now, if we move on and sum the forces in the parallel direction, note that the driving force here is the parallel component of the force of gravity, and that is equal to the mass times the acceleration of the block down the incline. Now, if we look in the perpendicular direction, we have the force normal minus the force of gravity acting perpendicular is equal to 0 because the block is not accelerating in this direction, so there is no net external force. However, we will be using this information and can show through summing the forces that the force normal is equal to the force of gravity multiplied by the cosine of theta, which we found to be 30 degrees. So if we now focus on the parallel direction and we go ahead and put in our values here for the force of gravity parallel, remember that's going to be equal to mass multiplied by the acceleration due to gravity sine theta. In this case here, look at what is on both sides of the equation. Mass. So mass cancels out in this instance here, and we can find the acceleration parallel and down the incline by simply looking at the acceleration due to gravity and multiplying that by sine 30 or 0.5 to find our acceleration. In the next part of this question, you will be using UAM to find the time. Now that we know the acceleration down the incline, we can use that information and the fact that the box is released from rest. Therefore, V naught is equal to 0, which means V naught T equals 0. We also know the distance down the incline to be 20 meters. So with all of this information, we're able to find the time it takes as 2.8 seconds for that block to reach the bottom of the incline. Question 42, we have a 10 kilogram object that is released from rest and it slides 20 meters down a 40-degree incline. We are also told that we have a coefficient of kinetic friction of 0.25. We are asked to find the acceleration of the block down the incline, and again we're asked to find the amount of time it takes for the block to slide to the bottom of the incline. So in this case here, if we were to sum the forces and do our free body diagrams here, we have our angle theta, and that is we are told that is equal to 40. So we have this object here, and it is at rest, and it's going to be sliding down this way, and the total displacement of this object down in parallel to the incline, we're told is 20 meters. We're also told that mu is equal to 0.25. Okay, so next we're going to sum the forces here. We know that the blocks is accelerating, or at least we assume it is based on the fact we're being asked to find the acceleration. So the force of gravity parallel is the driving force down the incline. However, friction, which always opposes the direction of movement, is up and parallel to the incline. And so when we look at our parallel summation, we end with this, where we have basically that parallel component minus force of friction equals mass times the acceleration down in parallel, which is what we're trying to find in part A. Now let's look at the perpendicular piece as well, where once again we show that force normal is equal to mass times the acceleration due to gravity times cosine theta. Okay, so we have a coefficient of kinetic friction, and as I've told you repeatedly throughout this unit, go ahead and write the physics is fun equation because you're probably going to be using it. And in this case, we are going to use it to find the force of kinetic friction. We're going to plug in our value for mu. We also know the value for force normal, which became clear once we summed. So we can take this and sub in here. And with that said, we're able to actually find the force of kinetic friction to be 19.2 newtons. And remember, that force is opposing the force of gravity parallel. So going back to the force of gravity parallel, now that we know the force of kinetic friction, which we found using the physics is fun equation, we can plug in these data into the equation, and we're able to solve for the acceleration down in parallel to the incline, which we chose as our positive direction to be 4.5 meters per second. In part B, let's use kinematic equations again to solve. We know the change in position to be 20 meters. We know it's released at rest, which means V naught equals 0, which means V naught multiplied by time equals 0. So plugging in our values and our newly found acceleration of 4.5 meters per second, we find that the time it takes to reach the base of the incline is 3 seconds. In question 43, we have a 30 kilogram box, and it is 20 meters up a ramp, and it is sliding with an initial velocity of 3 meters per second 3 meters per second up the ramp. This is a little different. The plane makes a 25-degree angle from the horizontal, and the surface does have friction, and we are told the coefficient of kinetic friction is 0.30. Part A. We're looking at the acceleration of the block down the incline. However, it's initially sliding up the incline. So we're going to need to think about that. And B, the amount of time it takes for the block to slide to the bottom of the plane. Remember, it's sliding up, and we're asked about when it slides back down. So we have a diagram here to help us conceptualize the problem. We're also going to talk about what's happening here. It's initially moving up the ramp, but it must be slowing. So it's moving up the ramp at 3 meters per second, but it's slowing down. So the direction of the acceleration must be opposite of that direction. Also note we really don't have any clue what caused that net force that sent this object moving up the incline, and quite frankly we don't care. We just know that the object is sliding up the incline, and we have a pretty good idea that this object will eventually stop and change direction, during which time the coefficient of friction, or the kinetic friction overall, will also change direction, and it will then move down the ramp. So this is a fairly lengthy problem here. Let's look at a series of free body diagrams, okay? First, we have the box as it's moving up the ramp, because it has this initial velocity. It will eventually stop Because there are two forces acting down in parallel in the opposite direction of the motion. So there will be a net external force on this object. We have the force of gravity parallel, acting down in parallel. We have the force of friction also acting down in parallel because it's acting in the opposite direction of the motion, which is currently up in parallel. Okay, if we look at then the next, there's 3 free body diagrams because we're going to really have to break this up into 2 parts. So these first 2 apply to part 1, and then these 2 will apply to part 2, basically, is how this will work out. So when the object stops and accelerates down in parallel to the incline, friction will change direction, and the force of gravity parallel is always going to be down in parallel up the incline. So there's a number of things going on here. So the best way to do this is, as I said, we're going to break this into 2 different parts. Because we'll have 2 different accelerations, and we've done similar problems, however, not quite this complicated. So we have to define our vertical direction. Well, we have our initial velocity and our initial change in position as positive. So for part 1, we're going to call up the incline as positive. So let's go ahead and move into our force summations. If you look here, we have our force of our forces acting in the parallel direction. We have the force of gravity and the force of friction acting downward, which means they're negative if we're calling up positive, up in parallel positive. So we have our acceleration that we're going to be solving for in part 1. And if you carry through and plug in the mass multiplied by gravity minus friction, we get to a good stopping point for the parallel. Now we're going to look at the perpendicular forces acting, and we have force normal being equal to mass multiplied by the acceleration due to gravity cosine theta. That's nothing new there. We've seen this in a number of problems for an object on an incline. Okay, now what do we have? We have the coefficient of friction, which means we're going to be using the physics is fun equation to find the force of kinetic friction so we can move forward to ultimately find the acceleration down the incline. So plugging in our values, you're given mu. We know mass multiplied by the acceleration due to gravity, and we also are given the angle of inclination as 25 degrees. So we have everything we need to calculate the force of kinetic friction, which is equal to 81.6 newtons. Okay, 81.6 newtons for the force of friction. All right, now we can go back to our parallel summation. Now that we've solved for the force of friction, we're going to be subtracting that value in our original parallel summation. So let's look back at our parallel summations here and plug in our new values. So we now are going to put in the mass. We also are now subtracting 81.6 newtons, which is that force of kinetic friction, which is acting down and parallel to the incline. And it looks like we have everything we need to solve this. And indeed, we can find the acceleration to be equal to negative 6.9 meters per second. Now, what does that negative sign mean? Well, it's telling us we have the object that's moving up in parallel, but the acceleration is down in parallel. And since we defined up in parallel as positive, the acceleration in the parallel direction is going to be opposite. So that's where the negative sign comes from. Okay, so remember, this is the acceleration that is slowing the object that is currently moving up the incline. So we need to find out, when does this object actually stop? When does its velocity equal 0? When does it change direction? How long does it take for the object to stop? These are all questions that can be answered using UAM equations. So let's look at one of many different approaches here. If we use velocity final squared equals v naught squared plus 2 multiplied by the acceleration and the change in position, and we acknowledge that when this box is at the top, when it stops, now the acceleration will still be there, but when it stops, its velocity equals 0. And we know its initial velocity to be equal to a positive 3 meters per second. We also now know the acceleration down in parallel to the incline, which means we can solve for the change in position. And so this box will go an additional 0.65 meters up the incline. Remember, it was 20 meters. It's going to go an additional 0.6, so its total change in position up and parallel to the incline is 20.65 meters. All right, so we know how far it'll go before it has stopped, and now we know what's going to happen. It's going to turn around and come back down the incline, and kinetic friction will change direction. Let's see if we can find the amount of time it takes for it to stop. It's going up. How long does it take for it to actually stop for these additional 0.65 meters? And we see that we can use v final equals v naught plus the acceleration multiplied by time, because again, we know the acceleration, we know v final to be 0, and we know v naught to be a positive 3 meters per second, which means we can easily solve for the amount of time it takes, and that is equal to 0.43 seconds. Now, as all good physics students will do, they will ask questions and possibly even go a little bit beyond what the question is asking by saying, what other UAM could I use? Or could I somehow double check my work here? Absolutely you can. Let's use the change in position is equal to a v naught t plus 1/2 at squared, where we now know x to be 0.65 meters. Okay? And, you know, if we look at this again and you plug in any of your values that you have, you will confirm that x is equal to 0.65 meters. So using a couple different approaches to make sure as we move forward into part 2 of this lengthy problem. Okay, so here's what we know. And as we move into part 2, we're going to start looking at our summations. And please, again, make note, direction of friction will change because that direction always opposes the direction of movement. So notice how our summation parallel has changed. We are now subtracting the force of friction from the force of gravity parallel, whereas in the last problem, they were acting in the same direction. So in this case here, we have they're opposing, and force of gravity parallel is indicated as greater in magnitude because we know this object will accelerate. There will be a net external force that will accelerate the object down in parallel to the incline. Okay, so that's a subtle but very important difference that has occurred in our parallel summation. Nothing's changed in our perpendicular summation, and nothing's changed with the force of kinetic friction except the direction. Mu hasn't changed. That's a property of the surface of the incline. The mass of the object hasn't changed, which could affect force of friction by way of increasing force normal, but that doesn't occur. Therefore, the magnitude of the force of friction remains constant. It is the same as in part A, or part 1 rather, of this problem. So we can take this and plug it into our parallel summation, and we can then arrive at a final answer for the acceleration of the object down the incline. Solving for the acceleration parallel, we get the value of 1.5 meters per second. So that is the acceleration down the incline. Okay, so next, let's use UAM equations. Let's find how long it takes for the object to slide down. Remember, it was 20.65 meters up. How long does it take to go down? And then in addition, how long did it take while it was going up? Because we're asked for the time it took for the block to slide to the bottom, that whole amount of time. So, we already knew the 0.43 seconds for it to continue going up before it stopped. Now let's find how long to go down. So we can use our change in position of 20.65 meters, and we can go ahead and calculate that total amount of time that it took. Okay, pretty cool approach. And there are other methods to solve this problem. But here we're using part one, everything we gathered from there. And ultimately, we're finding that from 20.65 meters up the incline, when it is stopped with an acceleration of 1.5 meters per second, we have 5.2 seconds. Okay. Whew. That was a great problem there. Question 44, where we're going to start using a system approach to find out some things about the forces acting within these two objects or the system. So two masses are hanging by a massless string from a frictionless pulley, and I've alluded to that in class. That'll become relevant when we start talking about rotational inertia, but for now, this is perfect. If mass 1 is greater than mass 2, all right, so mass 1 is greater than mass 2, determine the acceleration of the two forces when released from rest. And we have no numbers, and that's perfectly fine. We're going to just essentially derive an expression for the acceleration of the system. First things first, if mass 1 is greater than mass 2, then when this system accelerates, it will accelerate like this. The M2 will accelerate up, M1 will accelerate down, and as a system, we're going to define our positive direction for the acceleration. Okay, now we have our free body diagrams here. Notice the magnitude of the free body diagram 1 of the force of gravity is greater than the force of gravity in free body diagram number 2. If we sum the forces for the system, remember our positive direction. We're going to have M1 multiplied by the acceleration due to gravity. What's slowing the system? This guy here is slowing the system, okay? This right here is slowing. This is the driving force for the system. And our force of tensions are actually going to be equal and opposite, equal in magnitude, opposite in direction throughout this entire string. So, one of the most common mistakes here using a system approach, which I always felt was very intuitive, this approach, was not adding the masses. So it's the mass of the system. And again, defining your direction and choosing a positive and being consistent and doing that in a smart way so you avoid double negatives and things like that. So if we are to then take this and rearrange this to solve for the acceleration of the system, we can go ahead and factor out the acceleration due to gravity, g, to clean it up just a little bit. This is our final answer. And even though there are no numbers, that's okay. This is the answer. Now, recall in class I mentioned that if you don't want to employ a system approach for some problems, you can look at the summations of the objects individually and then algebraically add those equations. So if we were to use that approach in this example, you can see I've summed for object 1, I've summed for object 2. Notice the direction I've still chosen as the positive direction. However, in the case of M sub 2, we are showing the force of tensions here, and those are playing a role. However, when we look at adding these two equations together, we can then see that the force of tensions are internal or equal and opposite. They're internal to the system, they're equal and opposite here, so they cancel out when we go to add M1G, and we're adding it to a negative, so subtracting M2G. These guys go away, and we end up with the exact same answer. So it's up to you which approach you would like to use, a system or summing the objects individually and then adding those equations together. In question 45, here we have some values. We're told we have two masses. This is an Atwood machine again, and they're hung on a frictionless pulley by a massless string as shown. Okay, how far, all right, I'm going to go ahead and underline that. How far will the 7 kilogram mass fall in 2 seconds? So I sense some kinematics and UAM in our near future. However, we need to find the acceleration of this system, and the easiest way is going to be by summing the forces for the system. But first, looking at our free body diagrams, and in this case here, you know, we see that this 7 kilogram mass object multiplied by the acceleration due to gravity, that's going to be our driving force, and there's a greater force there, and that will lead to a net external force and an acceleration for the system. Let's go ahead and use a system approach to sum our forces, and we're going to define the positive direction as this way this time, which should be very intuitive because this has a greater force on the system. So this will accelerate. The 5 kilogram mass will go up, the 7 kilogram mass will go down. So you can see here with the summation, I've gone ahead and taken this, the acceleration due to gravity is factored out, which, you know, we showed that in the last problem, but it didn't have any numbers. And so we're essentially saying the difference between the masses and then that quantity multiplied by the acceleration due to gravity. But please do not forget to add the masses. So 12 kilograms is the mass of the system, and we can solve this expression quite easily by just plugging in values, solving for acceleration. We know the system will accelerate in the positive direction 1.67 meters per second. Now, once again, I'm going to show you this for a couple problems. If you are using the approach where you are summing for the individual objects, you would get the following equations for force 1, force 2. Then when you add these two equations together, 70 minus 50, you get 20 newtons, and that is equal to 7 plus 5, or 12 kilograms. And dividing the left side by 12, you get an acceleration, the exact acceleration that we obtain using a system approach. So that's up to you. Now, I told you, you knew we were going to be using some kinematics and UAM. So questions like how far? So what is the vertical change in position? How many seconds? So we're given the amount of time. So we want to find the change in vertical position. So like we always do with kinematics, we write down everything we know and we choose from one of the 4 UAM that fit our variables the best. Okay? In this case here, we can use the change in vertical position equation that you see here, because V naught T will go to 0, okay? So V naught in the vertical direction is 0. That means that piece goes away, and this turns into a very simple equation to solve for the vertical change in position of 3.3 meters. So this is a substantial, I always ask you this. So 3.3 meters, my goodness, that's like over 10 feet. So this is a large Atwood machine. All right, this is a very large Atwood machine, so it's good for you to always step back and do those reality checks on these problems. In question 46, now we have a modified Atwood machine, and we have our two masses connected by a light string over a massless pulley, as shown. Assuming this surface is frictionless, find the acceleration of mass m. Okay, well, the smaller mass, which is indicated with a lowercase m, it will have the same acceleration as the larger mass, m, because they are a system. They are connected by a light string. So let's look at our free body diagram for the larger object. Okay, summing the forces there, we have forces acting perpendicular to the surface. And then we also have our force acting in the x direction to the right, the force of tension. If we look at free body diagram 2 for the smaller object, we only have two forces acting. Mass gravity, and then that force of tension, which will be equal in magnitude opposite of direction of the other force of tension, because this is the same string, and thus the force of tension is constant throughout. It is the same throughout. We're going to choose a positive direction, and if this accelerates, we're going to see this. So let's choose that as our positive direction. I'm going to go ahead and rewrite that because that looked like a 9. So that's our positive direction. And so we're going to sum the forces for the system. So what is the driving force? This right here, mg. All right, that's going to be our driving force, force of tension. Now, we do not have friction. However, we do have an object, and that object does have mass. So looking at our total summation, we're going to see that force of tensions go away, and we end up with something quite simple. However, if you do not remember to add the larger mass, capital M, then you're going to get an incorrect answer, because this system is composed of masses that are two masses, and you have to add those together ultimately. Okay, so the final value, if we factor out the acceleration due to gravity, or little g, we end with this expression here. Now, if you choose to sum forces using an object approach, you can do so. And for object 1, we'll have mg minus force of tension, and that's the lowercase m, the smaller mass. And for object 2, we have the tension force. I want you to look here. Look at what's acting on this. Just this one tension force is acting in the horizontal direction. Students are often tempted to start saying there's capital T, or tension minus something, there's friction, right? No, there's no friction. So there's one force. Please do not make up forces acting for object 2 in the horizontal. And that's going to be equal to the mass of that object, capital M, multiplied by the acceleration of that object, which is the same regardless of which object. So if you look at these and add them together, these two equations, you end up with this expression. Simplifying this, you get the exact same answer that we obtained using a system approach. It's up to you which one's easier. 47 here. Here we have another modified diagram, but we have a hanging mass and we have a cart of mass M1, a 2 kilogram cart, and the wheels are jammed up on this cart, so it's not able to roll. So it shouldn't be a surprise. We have a relatively high coefficient of friction of 0.5. And we're asked to find the acceleration of the system. Okay, so if we look at the objects and we look at the free body diagram for object 1, which is the cart, we have our objects acting perpendicular to the cart track, rather, the surface. And we also have two forces acting horizontally on the free body diagram. We have the kinetic friction opposing the direction of motion, and we have a force of tension. Let's look at our hanging mass. Only two forces there. The force of gravity for that second mass and that tension force. And the tension force here is going to be the exact same as the tension force horizontally on the cart. So, summing the forces for the system. What's driving the acceleration? This right here. Okay. What's opposing that motion? The frictional force is opposing. The tension forces are internal to the system. They will actually cancel out. We can go through the motions and show that. But we also need to acknowledge the mass of the cart in our summation using a system approach. So we're going to be adding those two together. All right. And when we look at the vertical direction, we've shown that the force normal is equal to mass 1 multiplied by the acceleration due to gravity. And we don't know the force of kinetic friction, but we're given mu, which means we're always going to use physics as fun. So using the physics as fun, we found the force of kinetic friction here to be 10 newtons. We were then able to take that value and plug it into our summation and say that the 100 newtons minus that 10 newton force was equal to 12 kilograms. Okay, so if we rearrange and solve for the acceleration of the system here, we can find that the acceleration of the system is equal to 7.5 meters per second per second. Okay, now if you prefer an object approach, sum each object individually. Note for the hanging mass minus the force of tension, and then also note for the force 2, which is for the cart, we have that force opposing, so a negative force of kinetic friction plus the tensional force, and when we add those together, force of tension cancels, and we end up with the same expression we had here. Okay, that is the same. And then if we solved that further, we would find, again, the acceleration would be identical to the system approach. All right, so in question 48, this looks like even more fun. We have a modified Atwood, and that Atwood is now on an incline. Okay, and there's friction. This is going to be a blast. All right, so let's think about what's happening in this problem here. Okay, so let's start with some free body diagrams. Let's look at mass 2, which is the object on the incline. We have a force normal. That force is going to always be perpendicular to the incline. Okay, so if we show from the center of mass, and then we have the perpendicular component of the force of gravity, which we can find using mg cosine theta. And we have a couple forces acting parallel to the incline. We have this force of tension here, and we also have an opposing force by the force of friction that's opposing the direction of the object, and we're going to say this object will be accelerating up in parallel. Therefore, the force of kinetic friction will be down in parallel. Okay, free body 2, for hanging mass 1, only two forces acting, and of course, that force of tension will be equal in magnitude to the force of tension in free body diagram 1. And so we have mass 1 multiplied by the acceleration due to gravity as our driving force for the system. Using a system approach, we're able to sum forces. We have already reasoned through, but the direction of our acceleration here is going to be in this direction. So M2 is up and parallel moving, M1 is down vertically toward Earth. And so if we subtract here, let me see, mass 1, and we're subtracting the tension force, and then we're adding it. So again, that's just showing you those forces are internal to the system. They cancel out. They are equal in magnitude. We have the force of kinetic friction opposing that. We also have another force down in parallel to the incline. And I should point out on this free body diagram here, notice the force of gravity has not been resolved into its parallel and perpendicular direction. So earlier, when I showed the force of friction here, I should have also shown the force of gravity parallel, and this being the force of tension, like so, for the resolved components, okay? I want to make sure you see that. I did not resolve this. If I did resolve it, I'd need to draw another free body diagram. I couldn't and wouldn't simply add them to the existing free body diagram. Okay, let's look at the perpendicular direction here. And we are given values for mu, so let's keep that in mind as well. This here is simply a reminder. You probably have this one down by this point, but just a reminder because I'm going to plug all of these in here to the summation and start solving this problem. So force normal is equal in magnitude to the mass multiplied by the acceleration due to gravity for object 2, and that quantity multiplied by cosine 25. Okay, physics is fun time because we know we need to find the force of kinetic friction given a mu of 0.2. So plugging in those values, we find the force of kinetic friction is equal to 3.6 newtons, and that is a force that is opposing the direction of motion. Now we can look at our system and plug in everything we know because we now have a value for the force of kinetic friction, and this value here is the force of gravity parallel with, and that's an opposing force in this system, and that's equal to the mass of the system, or 8 plus 2, and now we can finally find the acceleration of the system to be 6.8 meters per second, and that's in the positive direction, which we defined. Okay? So now if we look at our summation in the y direction, we can also show here that the tension force, because that is the big change here, the force of tension. And you've heard me say in class, use a system approach to find the acceleration of the system, and then you can analyze each object individually, okay? So, and that's what we're doing here. I've also asked you to say, what would the force of tension be if this object were not moving? In other words, what would this force of tension be if this object were at rest? Okay, so we have M1G and then we have T. It's in a state of equilibrium, which means M1G is equal and opposite to the force of tension. So mass 1 in this case is, our mass 1 is 8 kilograms, so 80 newtons should be the force of tension when mass 1 is at rest. That was 8 kilograms multiplied by 10 meters per second, okay? So 80 newtons. However, it's accelerating in the direction and the direction of the acceleration is the same as the acceleration due to gravity. So let's make a prediction about what the tension should be. Should it be greater than or less than 80 newtons? Let's find out. Indeed, we find it's quite a bit less than. And we've talked about this in our elevator problems for contact force, apparent weight, force normal, but it makes sense. Remember the example I went over in class with the rope over the cliff. Okay, so we are subtracting the acceleration in the vertical direction from the acceleration due to gravity. So we're taking that value, which we found using a system approach, and we're subtracting it from 10 meters per second per second. So the force of tension is it's much less than the predicted 80 newtons. Okay, 80 newtons is the force of tension when the object is at rest or state of equilibrium. Here, it's much less than that. And the opposite would be true if it were accelerating upward. We'd be adding that vertical acceleration to the acceleration due to gravity. So our answer would be greater than 80. I would encourage you to make up some numbers and throw them in and prove that to yourself at this time. Question 49. This question has 3 parts. And for each part, we are finding the force of tension when that is applicable in the rope and the acceleration of the set of masses, i.e. the system. Okay, and we're told these are the values we will plug in for all of these. So let's start with scenario number 1. Okay, we have a force acting to the right on an object of mass m on a frictionless surface. Please don't make up forces here. Okay, please do not make up forces. There's no frictional force, so you don't have an opposing force from friction. Okay, so for part 1 here, summing the forces, the force of the system, pretty simple system, is this one object, which is a force to the right, and that is equal to the mass, in this case, of this object, capital M, and the acceleration. Our system is very simple here in scenario number 1, and so the acceleration is 10 meters per second per second, all right, caused by a force of 10 newtons acting on an object of mass 1 kilogram. Okay, let's move on to something a little more challenging. So here we actually have a system composed of 2 objects connected by 1 rope here, and that same force acting to the right. Consider it like a force applied, if you would like. Some sort of force, contact force to the right. Okay, so in this case here, we have our force to the right, and if we're doing the acceleration of the system on a frictionless surface, there are no opposing forces. However, we do have that mass of the system we need to take into consideration. Okay, so our force is 10 newtons. We're not going to make up any fictitious forces, so that one force is equal to the mass of the system, which is equal to 3 kilograms. Therefore, the acceleration of the system, which is composed of 2 objects to the right, is 3.3 meters per second per second. Now we can go ahead and use an object. So let's consider an object. We want to know the force of tension here. Okay, so if we were to do that, we would look at the forces on this one object, and the tension force, which is the force acting to the right, and that force acting to the right, you need to just look at what's happening right here. Okay, this is the force of tension. It's acting to the right. We have no friction, so we don't have any forces opposing this motion. And for that reason, the force of tension is equal to 1 kilogram multiplied by the acceleration, which is the derived unit for newtons, okay? Kilograms multiplied by meters per second per second. Okay, so now we know the force of tension. Let's move on to an even better scenario, 3. Okay, so first and foremost, what is the acceleration of the system? Okay, so we're going to go ahead and look at our force applied, which is 10 newtons. We're not going to make up any other forces because the opposing forces here, there's no friction. We're going to compensate for that because we're finding the mass of the system. So 10 newtons is equal to 3 plus 2 plus 1, or 6 kilograms, and multiplying both sides by that system mass, we get an acceleration to the right of 1.7 meters per second per second. Now we can move in and find some information using an object approach. Okay, and one of these objects is actually a system. So let's look at force of tension 1 here. All right, so here we have, and this is T1, okay, and to the right. And so when we look at the force of tension 1, again, we're not subtracting anything, we're compensating. We're using a system approach again, even though it says object. This object is composed of, this system is composed of 2 objects. So here, conceptualize this. Let's just do this. So that way I can avoid some of this esoteric language I'm using. This is one object of 3m moving to the right. How does that sound? So now we have the sum of the forces for the object. The mass of that object is 3 kilograms. We found the acceleration using a system approach, so we can say T1, which is this force of tension here, is equal to 5.1 newtons. Okay, now we can actually find this final force of tension here, which is this guy here. We'll call T sub 2. And so looking at T sub 2 and our already known acceleration of 1.7, we find the force of tension to be 1.7 newtons. That's 1 kilogram multiplied by the acceleration of the object. Okay, so we have answered all of those questions and we're ready to move on to problem 50, which has 3 different scenarios. Okay, and these scenarios we're going to call 10, 11, and 12. We're also given some values, and yay, there's friction. So we're going to be using that value as well. Okay, first and foremost, how are we going to find the acceleration for these sets of masses in these 3 scenarios? You guessed it, using a system approach. Then we'll use an object approach, analyze the objects individually to find what is being asked for as well, which is the force of tension. Let's start with scenario 10. We're going to sum the forces for the system, okay? And the object is going to accelerate. In fact, all of them will have the same direction of acceleration, okay? And the net driving force on this system will be the 2mg, okay, or the force of gravity. So in our summation here, we have our force of gravity subtracting the force of kinetic friction, okay? So force of kinetic friction, we're going to say, okay, the force of kinetic friction is equal to mu force normal. And so you're able to solve for, which we've done so many times in class, you're able to plug in your value for mu, and also to acknowledge that for an object on a surface here, force normal is equal in magnitude to mass gravity. Okay, so having said that, we're able to plug in here mass gravity is equal to force normal, and then we're able to ultimately plug that in there to show. So physics is fun. Once again, proves to be incredibly useful here. All right, so now let's look at the objects. What's the force of tension? So now we're being asked, what is this force of tension? And we're going to conceptualize the problem. We're going to make a prediction based on the direction of the acceleration. That force of tension would be less than what it normally would be, which would be 2 kilograms multiplied by the acceleration due to gravity. It'd normally be 10, but in this case, it's only 8. All right, now we've gone over this repeatedly, starting with our elevator problems and several of the last questions, if you're not quite following me. But we're taking little g and we're subtracting the acceleration in the vertical, or 6 meters per second, to get this value here. Scenario 11, force of the system. Okay, we have 2 hanging masses here. And so if we combine their masses, we can find the system acceleration, which will enable us to move on and find the force of tension for both of these sections here. We'll find it here, we'll find it here. And so what's the driving force? It's 5. Where did 5 come from? 3 plus 2. Think of this as one object. If that helps you out, think of this as one object. All right. Minus, what's opposing it? Force of kinetic friction. What's the force of friction? Mu multiplied by force normal. What's force normal? Force normal is equal in magnitude to mass multiplied by the acceleration due to gravity. So that's where all of this comes from. And don't forget the system of 6m. All right, so we have the system, we have this and this moving together, connected by a string. So that's where 5m plus m comes from. So we finally get the acceleration of the system to be 8 meters per second. Now, let's go in and look at the objects, okay? So for the first one here, we're going to call this the tension force 1, and we have 2 mg minus that is equal to 2 mg. Okay, so this here is what we are calling the tension force number 1. All right, and we are showing that tension force to be 4 newtons. Now, what would that force be if it were not, if it were at rest? It'd be 2 times 10, it'd be 20 newtons. Here, it's only 4 newtons. So now let's find out about our other force of tension here. Okay, if we look at the next piece of information, and we look at 12, or excuse me, we look at, sorry, I got ahead of myself here. If we look at our other tension force, which would be this one here. So I want you to conceptualize that as one object, and that one object has a mass of 5m, or 5 kilograms, and it's the force acting there would be that quantity multiplied by the acceleration due to gravity. And we have our tension force, which is in the opposite direction of the system. So we're going to subtract it. We have the mass of the object, which is really 3 plus 2. And we already know the acceleration of the system, so we know that the acceleration is shared for all objects in this scenario. So we are able to solve for the force of tension right here. Now, my question to you would be, what would this normally be if the system were at rest or in a state of equilibrium, which could be a constant acceleration? But if it were at rest, what would this be? 50 newtons. 50 newtons. 5 times 10. So 50 newtons. However, it is 1/5 of that because it is accelerating at, 8 meters per second. So we're subtracting that from the acceleration due to gravity. Okay? Last scenario for question 50. This is different. We have two objects. They're connected by a string. We're going to use these same values, but we're not incorporating mu because there's no objects in contact with that surface. So we won't be using physics is fun. Darn. Instead, we're simply going to look at, really just pick which one will this move. Well, this system rather, will have a positive direction to the left and down for the 3 kilogram mass. So what's opposing this acceleration would be this mg here, okay? Internal would be the forces of tension, which we can find here in a minute. But first, we found the acceleration due to gravity. So 30 newtons minus the 10 newtons, dividing that quantity by the mass of the system gives us positive 5.0 meters per second. So now let's go in and let's find the tension force here, which is going to be the same for both. But let's go ahead and look at what that's going to be. All right, so we're going to analyze the forces acting on this object. So in the y or vertical direction, we have 3m multiplied by the acceleration due to gravity minus tension, because that's in the opposite direction, is equal to the mass of that object, or 3 kilograms. And we found the acceleration using a system approach of 5 meters per second. So we're able to find the tension force to be 15 newtons, which if this object were at rest, it would be, 3 times 10 equals 30 newtons if it were at rest, just hanging there. But it's accelerating at exactly half the acceleration due to gravity, which is 5. And so it's no surprise that the force of tension is exactly half what it would have been if it wasn't accelerating. So pretty cool problem here. Now this question gets at the drag force and terminal velocity, which oftentimes will pique students' interest. And the concepts are quite simple, so I do mention them, and you've read through and you understand for that. We're going to look at, the size of the object, that cross-sectional area, and the mass, and there's some other variables that come into play for this idea of air resistance and drag, the force of air on an object. But let's look at these motion time graphs here. So foremost, we have g, little g, the acceleration due to gravity. And so initially that acceleration will be 10 meters per second. But what is happening here is the acceleration due to gravity, it's changing. It's getting less and less over time. And eventually the acceleration is becoming constant here. Okay, so a sentence describing this might be: the acceleration starts at little g and over time declines to 0. It reaches 0 at terminal velocity. Okay, now let's look at our velocity as a function of time for an object in free fall. Over time, we see that the rate here is changing. In fact, it's getting less and less and less until we get a slope of 0 here. So when a slope is 0 on a velocity time graph, that's telling us that the velocity is constant. When is velocity constant? When an object in free fall reaches the terminal velocity. Okay, so here's a sentence that may describe this scenario. The velocity starts at 0, okay? For an object, it's 0, and then it increases and increases, but at a decreasing rate, as shown through this series of tangents here. The rate is decreasing. However, when terminal velocity is reached, that rate remains constant. The slope is 0, so we have terminal velocity. Lastly, we have the vertical change in position as a function of time for an object in free fall. And notice what's happening in this case here. We have if we were to draw our tangents, let me come over here where it's a little more noticeable. They are increasing, they're getting bigger, slopes getting steeper and steeper and steeper, okay? But when we reach terminal velocity here, which is not indicated, but if we were to continue this, we would continue it like this, where that slope was constant. So let's see what that looks like. The vertical displacement starts at 0 and increases, and it's increasing as speed increases, okay? So look at the velocities increasing, and so the vertical change in position is increasing until terminal velocity is reached. When terminal velocity is reached, we have a constant velocity and thus a constant positive slope for the vertical position as a function of time. Pretty cool stuff there. In question 52, we have a scenario, a series A through H, various arrangements of wooden blocks. And this is an assessment for Newton's third law, action-reaction pairs. We're given the mass, and we see there's a number of arrangements. We're told they're not moving, but they're on inclines, they're stacked, they're touching each other horizontally, they're stacked on top of one another vertically. So ostensibly, this looks like a very challenging problem. However, in the end, remember that in a force pair, those forces will be equal in magnitude, opposite in direction. So regardless of what these forces might be, some we can calculate, some we cannot, because we do not know information about several of these arrangements that would allow us to calculate it. They're all the same. Within a given pair, the differences will all be the same. Okay, looking at this here, like, you know, there's a contact force here, there's a force here, all right? Well, what would this force be? That's what I'm saying. Some of them we could calculate, all right? So we'd say 0.2 kilograms multiplied by 10 equals 2 newtons, okay? So the box A in scenario C is exerting a downward force on box B, magnitude, or really magnitude and direction, 2 newtons. Box B is exerting an upward force normal to the box. Box B is exerting a 2 Newton force upward. Now, what if you looked at this force here, which it doesn't even ask about? I'm just having so much fun right now, I want to talk about it. Well, you could conceptualize this as one object of mass of 4/10 of a kilogram multiplied by 10. So here we would have 4 newtons. So boxes A and B collectively as a system are exerting a downward force on this table or whatever of 4 newtons, and that table is exerting an upward force perpendicular, which is actually force normal, of 4 newtons upward. And you can go through every single scenario, no matter what the force is. Force A on B, well, the force B on A will be the same, just opposite direction. So if one is down and parallel to the incline, the other one will be up and parallel to the incline. If one is to the right, then the other is going to be to the left, but of the same magnitude. Okay, so all of these arrangements are the same. And that takes us through the entire Unit 2 problem set. So I'll see you guys in class.